What's up, guys? In this video, I went through my back catalog and hand selected the exact videos that I want you to watch to be able to have a better understanding of rational expressions. We'll start with being able to simplify a rational expression by factoring, identify the discontinuities such as wholes as asymptotes. We'll deal with adding and subtracting as well as multiplying and dividing rational expressions, including complex fractions. But don't worry, we're also going to talk about how to graph a complex fraction as well as how to solve and be able to identify any extraneous solutions. So by going through this whole video and all 44 of these examples, I can guarantee you by the end, you are going to have a better understanding of rational expressions. I look forward to seeing you at the end. Cheers.
Well, that's what we're going to do. We're going to start with some very basic ones, and then we're going to move our way up. Now, the one thing I want to make sure that we do not do, per our discussion, guys, when you have the exact same term over the exact same term, you can divide them in there. The one thing you guys do not want to do is I do not want to see this. Okay? You can't divide this 4. You can't separate across addition. You can't take this 4 and say, oh, I'm going to divide that into both of those. Okay? Do not do that. All right? Now, what we can do, though, what we're going to practice, the reason why I got you guys started practicing with factoring is we need to practice factoring. To simplify these, as you guys can the difference from today and last class period is last class period we didn't have any addition or subtraction, right? Everything was multiplied or divided, correct? Now we have we have terms that are separated by addition or subtraction. So we have to be careful. So to simplify them, what we're going to do is factor. So we look at our numerator and we say, how can we factor 4n plus 16? First thing we always want to do is see if we can factor out a GCF. Is there a common factor we can factor out of 4n and 16? 4. So therefore, I factor this to 4 times n plus 4 divided by n plus 4. Now, the next thing we need to talk about, though, is we need to talk about restrictions. So Dave, here's something I really, really want to make sure you understand. Remember how we talked about, guys, when we did this example, 5 divided by 0 equals x? We know that 0 cannot be in the denominator, right? Yes. We know we cannot have 0 in the denominator. So therefore, I take my denominator and I say n plus 4 equals 0. What value would make my denominator equal to 0? Negative 4. So n equals negative 4. So when you guys find your answer, you're going to say n cannot equal negative 4. Because again, what if I take negative 4 and I put it in for n? Negative 4 plus 4 would equal 0, meaning we would have no solution, right? So even though we're simplifying, we're adding in this restriction. So now, is there anything else I can simplify? Anything else I can divide into 1? No. What about n plus 4 divided by n plus 4? That divides to 1, correct? So therefore, my final answer is 4, where n cannot equal negative 4. That is what your final answer. Welcome, ladies and gentlemen. So what I'd like to do is show you how to simplify a rational expression by factoring using our special factoring techniques, which include the difference of two squares as well as a perfect square trinomial. Now, that doesn't mean we're going to have to forget factoring out a GCF, which we're still going to use. But the main important thing is not only just factoring, but understanding the division property as well as when to apply it and constraints of our denominator, which, again, I'll talk our way through. But the main important thing is when we're looking to simplifying a rational expression by factoring, we're going to look in the numerator as well as look in the denominator and see what exactly can we factor. Well, when we're looking into factoring, first thing we always want to see if we can factor a GCF out, anything that they have in common. And in the numerator, they have nothing in common, so I can't factor this by simplifying it anyways. However, in my denominator, you can see that I have x squared minus 4. I can't factor out a GCF. However, I can use the difference of two squares to factor this. So therefore, I'm going to have x plus 2 divided by, now when I factor this using the difference of two squares, I'm going to have x plus 2 times x minus 2. And now you can see that the expression x plus 2 is the same in the numerator as well as the denominator. And since in the denominator it's separated by multiplication, I can apply the division property. So therefore, those are going to divide to 1, and I'm just going to be left with 1 over x minus 2. Now, when we write it now, if I want to write my constraints, I can say x minus 2 cannot equal 0. So the values that x minus 2 is going to equal 0 is going to be at 2. So I'll say my constraint is going to be x cannot equal 2. now going over to this example here, now in my numerator, I see that I have a binomial. And of course, it's a square, and it's the difference. So I know I can simplify using the difference of two squares. So I'll factor that out by x minus 4 times x plus 4. And that's what the difference of two squares is really helpful for. You can factor it very, very quickly. When looking at my denominator, though, I don't have a difference of two squares, but I do see that I can factor out using the GCF. 2x and negative 8 both share a 2, so I'm going to divide out the 2. And when I do that, I'm left with an x minus 4. Again, making sure that we notice that our expressions are separated by multiplication, I can now divide out the x minus 4s, and therefore I'm left with x plus 4 divided by 2. And then I don't need a constraint here because I know 2 is not equal to 0, and that would be my only constraint is if I had a variable in there, I just have to say that it cannot equal 0. All right, so now in the next example, we again have another difference of two squares. It's very kind of obvious. Once you work through a lot of these problems, you can kind of quickly see them. So I can factor this out. I know that 5 times negative 5 is going to give me minus 5, and they're going to add up to give you a 0 as a middle term. So I'll factor that out. And then now I have a perfect square trinomial, which again, you can see 25 makes your perfect square. But instead of having no middle term, I now have a middle term negative 10, negative 10x. But I understand that if I wrote this as a perfect square trinomial, which would be x minus 5 times x minus 5, though when I FOIL this out, it's going to be that perfect square trinomial. So again, this is just through a lot of practice of knowing how to factor perfect square trinomials. Well, what's nice about at least using this again is you can see that since they're separated by multiplication, I can apply the division property, and the x minus 5s will divide to 1. So I'm left with x plus 5 divided by x minus 5, where x cannot equal a positive 5. Because if I had positive 5 in there, if I put a 5 in for the x, then 5 minus 5 would be 0, and I'd have my denominator equal to 0. So I'm just writing in that constraint. All right, in this last example, this one really gets students confused. And actually, it's the exact same type of problem as this one. The only difference is I need to factor out a GCF first. So what I notice here is I have some terms that have some common, or I have expressions that have common factors of them. So in the numerator, I can factor out a 2x. So when I factor out a 2x, I'm left with x squared minus 4. In the denominator, when I factor out a 2, I'm left with an x squared plus 4x plus 4. And now we can see that first, these 2's, those divide out using the division property. Here is another example of difference of two squares. So I have x times x minus 2 times x plus 2. And then in my denominator, that is an example of a perfect square trinomial, which would be x plus 2 times x plus 2. Again, you can see that each expression is separated by multiplication. So therefore, these two expressions can divide out. And I'm left with x times x minus 2 all over x plus 2, where x cannot equal negative 2. Because again, that would make your denominator 0. And there you go, ladies and gentlemen. That is just your basic technique for simplifying rational expressions by using your special factoring techniques. Thanks. All right, so in the next example now, we're upping the ante on our factoring. So now you guys can see we have a trinomial over another trinomial. So when Tyler's looking at this problem, basically what we're going to do is we're going to break this up, ladies and gentlemen. And you're basically just going to want to simplify your numerator and denominator separately. All right, and that's really the best way I can pretty much tell you is you're going to want to factor this. And that's why the factoring techniques come so important of thinking about the terms that multiply. Now, I will do one the long way, and then I'm going to do one kind of the shorter way. Because obviously, ladies and gentlemen, the more and more practice you get with this, the better we should be doing at doing this in our head. So in the first one, though, let's just do this the long way. If I wanted to factor this out, I would do a times c and b. What two numbers multiply to give you a times c, but add to give me b? Remember, a is our coefficient of x squared, and c is our 2. So we have 2. And then our middle term is negative 3. So we think about what two numbers multiply to give you 2, add to give you negative 3. Well, those factors are obviously negative 1 and negative 2. Now, since a is equal to 1, I can write these as my factors, right? If a was not equal to 1, we would use the box or the grouping technique, which we talked about, which I'll go over again later in the class, or at least in my next example. So therefore, I can rewrite this one as x minus 1 times x minus 2. That is the factored form. All right? On this one, I'm going to start doing these in my head to kind of help you guys out as far as what I'm thinking. Again, basically what I'm doing is since a is 1, I'm thinking what two numbers multiply to give me negative 6, but then add to give me positive 5. Well, obviously, if two numbers are multiplying to give me negative, one has to be negative, one has to be positive, right? And if they're adding to give me a positive, that means the larger of the factors has to be positive. So what I come up with is x plus 6 times x minus 1. And let's double check that. Does x times x give you x squared? Yes. Does 6 times negative 1 give you negative 6? Yes. Does 6 times x plus 1 times negative 1, or x times negative 1, which would be negative x plus 6x, does that give you positive 5x? Yes. So now that's my factored form. Now that I have it in factored form, is it easy to identify what my restrictions are, what cannot equal 0, or what my polynomial cannot be, so the values equal to 0? So Taylor, what is one value I cannot have? Well, if you put in negative 1 for there, negative 1 minus 1 would give you what number if I plugged in for x right here would make this 0?
0?
Yep. What plus 6 would make that 0? Well, 1. 1 plus 6 gets 0. What number plus 6 would make that 0?
I don't get what you're doing down there,
All I'm asking you is what value it would make this, what value if I plugged in for x would make this 0? So what number plus 6 gets to 0? Does 2 plus 6 make 0? Does negative 2 plus 6 equal 0? Does 6 plus 6 equal 0? Does negative 6 plus 6 equal 0? Yeah. So basically, you can see it's really just the opposite of that. So you could say x does not equal negative 6. And then what should x not equal here? Positive 1. Does that make a little bit more sense? OK, sure. So now we have our restrictions. And now we just need to determine what can we simplify? What can divide out? And we look at these, and we pick on Jamie, and we say that, Haley, what can divide out here? We have some problems with this. Haley, what can divide out here? Jamie, can you help her out? The x minus 1s. Those divide out. They don't need to be right under each other. They divide out. So therefore, our final answer is x minus 2 divided by x plus 6, where x cannot equal negative 6 and x cannot equal positive 1. This example, ladies and gentlemen, this is asking a simplifying problem. So if you guys remember my operation for you, basically we need to identify, when doing these, we want to make sure that we can simplify, Christiana, the factors. So basically, we want to factor the numerator and factor the denominator. That is going to be true for all of these problems. So if you guys take a look at this, I have x squared plus 3x minus 18. We need to go ahead and factor. So again, this is a trinomial where a is equal to 1. So I basically need to find what two numbers multiply to give you negative 18 and add to give you 3, positive 3. Well, I can determine that that factored form is going to be this. Because I can verify 6 times negative 3 is negative 18. 6 plus negative 3 is positive 3. Then over, I have x squared minus 36. That's a difference of two squares. Would be x minus 6, x plus 6. Then we can apply the division property whenever we have a number or a term or an expression that's exactly the same in the numerator and the denominator. It divides to 1. Remember, they have to be exactly the same. You can't divide x plus 6 and x minus 6. They have to be exactly the same. So therefore, your final simplified answer is x minus 3 divided by x minus 6. Right? Okay, let's go. Now, basically, ladies and gentlemen, on this problem, what we have is x squared minus 4x plus 4 divided by 2x squared minus 7x plus 6. Now, when doing a problem like this, again, we have to go back to our factoring. Fortunately for you guys, we took a test couple class periods ago on solving quadratics, right? And basically, it's the same thing. We're going to need to practice this. So on both of these, it doesn't really matter which one you do, but we need to factor this. Now, obviously, ladies and gentlemen, we'd like you to be able to get to the point where you can factor these in your head. But I understand that, as of right now, you guys still need some practice on doing these. So basically, what I'm going to do is I'm going to do the long method for both of these. So therefore, we can at least see, again, remind ourselves how to do these. So the first one, again, remember, we always do a times c and b. Multiply, add. A times c, and then b. multiply, and add. So basically, if you're in this example, which I'm going to do over here, my a is 1, right? So I do 1 times 4, which is 4. And then my b is going to be negative 4. Over here, I have 2 times 6, which is 12. And my b is negative 7. Does everybody follow me? OK. So now what we need to do is identify what two terms multiply to give me 4, but then add to give me negative 4. Negative 2 and negative 2. Everybody agree with that? OK. Now the next one is what two numbers multiply to give me 12, but add to give me negative 7? Yes. OK. So there's two different ways to kind of do this from here. All right. Now I'm going to kind of show you the shortcut once we get to this problem. But I want you guys again to understand why do we do this diamond method? Because basically what this allows us to do now is for us to rewrite the equations like this: x squared minus 2x plus 4. Or in this one, I could write this as x squared, 2x squared. 2x squared minus 4x minus 3x minus 7. Does everybody see what I've done? I have now taken these terms that I've found, and I've replaced my middle terms for both of my trinomials. Does everybody see that? Because I'm trying to factor them. All right, if that doesn't make sense to you, let me go and try to do this. No, it's OK. It's OK. Hold on. I'm going to get through it's going to make more sense once we get to it. The other thing, remember, what is factoring? Factoring is writing this as a product. So this represents an area, right? An area of a box. So since it represents an area of a box, let's fill in the areas. X squared and 4. 2x squared and negative 7. Now, just like I added my blue areas here, I can fill these areas with a negative 2x and negative 2x. No, you do not have to do the box. OK? But what I want you guys to understand, what I want you to be able to visualize with this is, do you guys agree that this area right here, everything that's inside this box, is the same thing as this written out? X squared, 4, 4. Negative 2x plus negative 2x is 4x. Do you see what I did? But I split it up in a special way so that it fits in those two boxes. The same thing over here. All of this is the same thing as that, right? OK, now, so there's two different ways to do this. We can go back to our grouping method, which I showed you guys at the beginning of class. In the grouping technique, basically what we're going to do, Stephen, is group the first two terms and group the last two terms. Group the first two terms and the last two terms. Then basically all we do is factor out the GCF, the term that they have in common. Here, my two terms have in common an x. So when I factor out an x, I am left with an x minus 2. Here, they have in common a negative 2. When I factor out a negative 2, I'm left with an x minus 2. So therefore, I factor them out as x minus 2 times x minus 2, which is really x minus 2 squared, right? Which, guys, could we have done that from the beginning? Do you guys notice that's a squared number? And 4 is a squared number, right? Sheldon, not please now. That's a squared number, and that's a squared number. Does everybody agree? And that is 2 times the square root of both of those. So that's actually a perfect square trinomial, which is like the example I showed at the beginning of class. However, yeah. No, I'm just trying to show you. You just show why I'm showing you the box in this way? Yeah, what I'm trying to show you is, yeah, you can use both ways. I'm trying to just organize.
Use the box, right?
Huh?
You can use the box.
Yes. Okay. And the box method, let's look at it again to see how the box method. What two numbers multiply to give you x times x? X and x. Yeah, what two numbers give you x squared? Thank you, everybody. X times what gives you negative 2x? Negative 2. X times what? Negative 2x? So x minus 2 times x minus 2, which is again the same thing, right? But what I'm trying to show you guys is by using the box, it doesn't matter if you use the box or this, but you're still going to get the same answer. So what is x squared minus 4x plus 4 factored? x minus 2 times x minus 2.
So I really don't have to learn how to do the other one.
Learn the other what?
The other one.
This method?
Yeah.
No, if you don't want to do that, it's fine. Unless you have, you have to know you have to know grouping. We will be having problems that are grouping. That's all this is grouping. So this is helpful to know. Okay. However, do you want me to skip this method and just go with the box here?
Yeah.
Okay. So what two factors multiply to give me 2x squared?
2x. Well, it's going to be 2x right there and then x over there.
And why would I want to use 2x over here?
Wait.
Or should I put 2x here?
Can you put the 4 over there and then the 3 over there? You know what I mean?
No, all right. Well, yeah, I see what you're doing. But all right, but let's just pretend. What should I put here? 2x or the x? X. Why would the 2x not work?
Because you can't do that. Yeah.
There you go. Very
I
good.
just did it differently.
Good. Yeah, that's fine. You switch those. That's fine. So you do x and 2x. X times what gives you negative 3x? Negative 3, 2x, negative 2. Right? So therefore, this is x minus 2 times 2x. Huh? I'm sorry. There's talking over here, so I can't hear you. Say that again.
It's supposed to be a 6.
Oh, yeah, it is a 6. Very good. I don't know where that came from. All right. So now.
It's a positive 6.
Yeah, you're right.
One more and you're done.
Hey, very good. I don't know where those came from. They came from, I don't know where. Oh, they came from, I was looking up there. That's why. So now we look at this and we say, all right, what two terms can divide out?
The negative 2.
X minus 2 and x minus 2. Those divide to 1, correct? However, my restrictions are still going to remain. X minus 2 equals 0, and 2x minus 3 equals 0. Remember, our solutions cannot be 0 in the bottom. So you can't say x minus 2 cannot equal 0. We want to know what are the values when what are going to make this 0? What's going to make this 0? 2. So you say x cannot equal 2. And what's going to make this 0? Add the 3, divide by 2. X equals 3/2. So x cannot equal 2, and x cannot equal 3/2. So now my final simplified version is x minus 2 divided by 2x minus 3. However, we want to include the restrictions that x cannot equal 2 and x cannot equal 3/2. Yes. OK, so here we go. Now we got some problems that are going to be really, really fun to look at this, because I know you see this and say, oh, a is not equal to 1. I hate these types of factoring problems. So that's OK. That's why we're going to do it. And I'm going to show you step by step how to go through each one of these. And I'll show you 2 different ways to do it. Obviously, the fastest way to do would be the factoring in your head. But I want to make sure I go through this step by step so you can at least understand what exactly we're doing. So before we even get to that point, we always want to look at, can I factor out a GCF in my numerator or in my denominator? And unfortunately, in both these cases, they do not share a GCF. Then the next thing I want to do is always look for special factoring techniques. And unfortunately, I do not have any special factoring techniques I can use. There's no perfect square trinomials or difference of 2 squares or 2 cubes. So I'm going to have to go back to the nice nitty-gritty and factor. So you notice that I have my 2 polynomials in the form of ax squared plus bx plus c. So to do this, I'm going to factor here. Let's do the numerator. And let's go ahead and factor the denominator. Now I'm going to do this 2 different ways. However, the first part is always going to be the same. When factoring a trinomial, when your a is not equal to 1, we need to make sure that we determine what our not just c is, but a times c is, and then what our b is. So we need to figure out the value of a times c and then b. So for my numerator, a times c is going to be equal a negative 24. And my b is going to be a positive 10. My a times c over here is, for my denominator, is going to be 6 times 6, which is 36, and then a positive 13. All right, so I'm not going to write out all the factors because I am going to try to speed this up a little bit for you. So when we look at this, we just need to figure out, all right, well, all the factors are negative 24. So since it's a factor negative 24, we know that one of the factors has to be negative. So what 2 factors multiply to, well, we already know the factors that multiply giving negative 24, but out of those factors, which ones add up to a positive 10? Well, our factors in this case are going to be positive 12 and negative 2 because they multiply giving negative 24 and add to give me 10. Over here, you say what two values multiply to give me 36, but add to give me 10. Now, both the factors have to be positive because rather than just multiplying to make us positive, they have to add to give us positive as well. So they both can't be negative. And those two factors give me 9 and 4. All right, so the first way we're going to do this is we're just going to simply rewrite it by using our new terms. So I can rewrite this as 8x squared. And then rather than using 10x, I'm going to use my two factors to represent that. So I could say plus 12x minus 2x minus 3. OK, so all I simply did is instead of writing 10x, I wrote 12x minus 2x. It's the exact same thing. But the reason why I do that is because now we can use the technique of factoring by grouping. And factoring by grouping we like because what we're going to do is we're going to split it up into two different groups. And then we're going to factor by the GCF. And a lot of us are used to factoring by GCF because that's what we first learned when learning how to factor. So I look at my first two terms and I say, all right, what do those two terms have in common? We could say they both share an x and then also a 4. So if I take a 4x and I factor it out, I'm going to be left with a 2x plus 3. Then over here, I can say, all right, well, whatever I want to factor out to this, I want it to be the same as that. And I'll explain that in a second why. So you say, what can you factor out? Well, you can factor out a -1. So when I factor out a -1, I'm left with a 2x plus 3. All right? So what we did is we said, all right, what is the GCF of this first binomial? And then we factored out the GCF of the second binomial. So when doing factoring by grouping, you do a GCF first, GCF second, and then you say, all right, what is the GCF then of everything? And you notice that this whole expression, this binomial, the GCF is going to be 2x plus 3. So now you factor out the 2x plus 3. And when you factor out the 2x plus 3, you're left with a 4x minus 1. So therefore, that's going to be now my new numerator, which is in factored form. 2x plus 3 times 4x minus 1. OK, so now we need to determine what the denominator is. And to do the denominator, I'm going to use the box method. And what the box method does is it goes by the understanding of multiplication creates area, right? If you look at this, if I say this times this gives me that, which is true, right? That's what we did by factoring by grouping. Well, you can understand if this is the length, this is the width, then this would represent the area. So let's just create a nice little box. So what we're trying to do is if I'm given an area, we're trying to work backwards and say, all right, what were the length and the width? What were the two values that we had to multiply to give us that area? So far in our area, we know that we have a 6x squared and a positive 6. But we have two boxes. Which one are we going to put the 13x into? Well, that's where this comes into play. Just like how I rewrote our middle term here, I can rewrite my 13x as 9x and 4x. All right, and that helps us fill in our boxes. Now we just need to determine what are the lengths of the box that create that area. So I'll just show you a little guess and check on why some things work and why some things don't. So let's look in the upper left-hand box. We know that 6x times x gives us 6x squared. However, 6x times what gives us 4x? Well, that's going to start getting into a fraction, right? We don't want to deal with fractions. All right? And what happens if you do it the other way? Well, x times 6x squared, yeah, that gives us there. And x times 4x would be a positive 4. However, 6x times what gives us 9x? Again, it's another fraction. So that's not going to work. Now, I know that the other two factors of 6x could be 3x, and 2x. However, notice that 3x is going to have to multiply by a fraction to give us 4x. So let's rewrite them the other way. All right, 3x times 2x gives us 6x squared. 2x times what gives us 4x? Well, that's going to be plus 2. And then over here, 3x times what gives us 9x? So that's going to be plus 3. So therefore, now those are my two factors. So I can rewrite them as 3x plus 2 times 2x plus 3. And there you can see that I have a binomial divided by the same binomial, which will result into 1, leaving me with a simplified rational expression of 4x minus 1 divided by 3x plus 2. So there you go, ladies and gentlemen. That is how you simplify a rational expression by using your AC method to factor and then simplify. Thanks. All right. I guess I'll stop joking. All right. I don't have a problem going ahead and solving a problem like this for you. But the main important thing I want you to look at is, when you guys look at it simplifying our trigonometric expressions, obviously we cannot apply our properties of exponents because, these are all separated by addition and subtraction. So we want to look into factoring. And, when looking at factoring, when we have these good old trinomials, I can say, all right, what two numbers multiply to give me 15 that are going to add to give me negative 8. You just keep on working through and you're like, all right, I got it in my head. I'll figure this one out. But then we get to one of these larger ones and you say, well, what do I do with a term like that? Well, when we have 4 terms, that's going to be especially in factoring technique that we're going to want to apply.
Please report to my office.
So to do a problem like this, what we want to do is apply the grouping technique. And if you remember the grouping technique, the way that it works is if we have our 4 terms, we're going to break up the first 2 terms and then the last 2 terms. Then what we're going to want to do is factor out each one of these terms by their greatest common factor. So if I look at x cubed minus 5x squared, I can see I can factor out an x squared. By doing that, I'm left with an x minus 5. Up top, for negative 3x plus 15, what I want to do is factor out, again, another common term, so I can factor out a negative 3. And I'm left with an x minus 5. And the important thing when factoring by grouping is that you want to make sure you factor out the same enough factors, so therefore you have your common factors out here that you can factor out again. So here you can see that in out of each of these 2 terms, right, because now they're separated by subtraction, you can see the only thing they have in common is an x minus 5. So when I factor out an x minus 5, I'm just left with an x squared minus 3. So now I'm going to rewrite my expression to have x minus 5 times an x squared minus 3. OK, and then what we do is we go ahead and factor this. Well, x squared minus 8x plus 15. You guys might be thinking at this and say, all right, well, what 2 numbers multiply to give me 15? What type of numbers multiply to give me 15, but add to give me negative 8? Well, that can be hopefully negative 5 times x minus 3. So therefore, I can say this is x minus 5 times x minus 3. Well, therefore, my x minus 5 divides into my x minus 5. However, we look at this, and a lot of you might say, oh, well, why can't the 3's cancel out or the x's and just be left with x at the end? This is x squared minus 3, and that's x minus 3. These are not same terms. They're separated by subtraction, so you can't divide one into the other but not into both. And unfortunately, ladies and gentlemen, that is just going to be our simplified answer for this expression. We cannot simplify this any further. So that will be our final expression. So there you go, ladies and gentlemen. That is how you simplify a rational expression. Thanks. On to this problem. So the main thing, the main thing we guys want to do is just look into factoring the numerator as well as the denominator. One thing I noticed in my numerator is I can factor out an x, right? All these terms factor out to an x. And the other thing I noticed is I really don't like dividing when my a, which the first term is negative. So I'm going to factor out a negative as well. So in this first term, I'm going to factor out a negative x. That leaves me with a positive x squared plus x minus 1. And that's not correct. That's supposed to be a 2. Sorry about that. Did I not write that in there? Yeah, oops. All right. In my denominator, I don't really, again, I'm not going to, yes? Huh? Oh, yes, thank you. OK, we're going to factor this again. In my denominator, sorry, I wrote out the factored form for the answer and didn't put it back in there. For my denominator, I'm going to want to rewrite this again without a negative in front. But I want to have this in standard form, right? You should always want the power to be first. But again, I'm going to factor out that negative. So I'm left with an x to the 4th minus 1. Does everybody see what I did? I kind of like swapped these. So it was negative x to the fourth plus 1, and then I factor out the negative. That's how I got to there. Okay? Now I can factor this a little bit further. You guys can see here that I have x minus 1 times x minus 1. Here, you can see this is a difference of two squares, but it's kind of been raised up, which is really a x squared minus 1 times a x squared plus 1. And can I further factor this down? Because again, look at what I have. I have a difference of two squares again. So I have a negative x times x minus 1 times an x minus 1 all over a negative x minus 1 times x plus 1. Now, could I further factor this down? I could across imaginary numbers, right? I could do that as x plus I, x minus I. But again, when we're looking for our domain, when we're looking for these restrictions, we're going to only be focused on real numbers. So there's really no other need to further this down. OK, so now I have everything in my factored form, at least what I need. Because, I mean, you could factor this down, but that's not going to matter, which I'll explain in a second. Now we want to see what simplifies. Well, we have these x minus 1 divides out. Yes?
When you factor out the negative x, wouldn't the 1 be positive?
Yeah, negative 2 and 2x.
That's supposed to be a positive. Yeah, thank you. That was my original problem, right?
Yeah.
So, OK. So crap. So that's supposed to be a negative. And that was a positive. Right? OK, there you go. So I still factor. OK, yeah. There you go. Sorry about that. But still, the factoring still makes sense. Now, these divide out, right? Because any term or number or expression divided by itself is equal to 1, correct? So my simplified final result is just going to be a negative x times x minus 1. No, again, guys, what's a negative divided by negative is just a positive, right? So I don't really need to worry about having the negatives there. And I'm just going to be left with a negative times x plus 1 times x squared plus 1. Now, the other thing is we got to go back and identify what were the values of x that could not be in my domain. And what we need to do is we need to go back and look at our original problem. Basically, what are the values that cannot be for x that would make my denominator equal to 0? Well, what we could do is kind of like what we did for the domain earlier. Like if I set each factor equal to 0, x squared plus 1, hopefully you guys would see that that's going to give you plus or minus I, right? Does it make sense for us to say I can't be in the domain? No, because I is a complex number, right? So we're only talking about real numbers. That's why this doesn't affect our domain restrictions. However, can x equal negative 1? No. What about x equals 1? Well, remember our unit on functions. If I have a whole or if I have an asymptote, are both those values not in my domain?
Yes.
Yes. So just because something gets simplified out doesn't mean it's not a restriction. What that means is just because you simplified out this x minus 1, that is still a restriction on your polynomial. So we would say x cannot equals 1 and x cannot equal negative 1. Because again, guys, go back up to our original problem. If I plug in a 1 or a negative 1, does that make my denominator equal to 0? If you plug in a 1 or a negative 1, 1 to the fourth power is 1. 1 minus 1 is 0. Negative 1 to the fourth power is 1. 1 minus 1 is 0. So you have two restrictions, even though the simplified result only is going to show one solution, or only shows you that one restriction. So all I'm trying to advise you guys is step 1 is a factor. But before you simplify it, identify your domain, identify those restrictions. Then you can simplify it, and then just write the restrictions at the end. OK? Welcome. All right, so in this video, what I want to do is show you how to add and subtract rational expressions. And when we're adding and subtract rational expressions, what that pretty much is telling us is how we're going to add and subtract our rational expressions that are going to contain polynomials. Not so much as fun with fractions. We liked adding fractions. Probably now you could say 1/4 plus 3/4. And you say, oh, well, the denominators are the same. So you say, well, that equals 4/4, which is equal to 1. On the occasion, sometimes we'd have an occasion where our fractions didn't have the same denominator. So in that case, what we had to do was simply find the common denominator, which in this case, my LCD equals 15. So then I'd multiply this side by 5/5, keeping my fractions equivalent by multiplying on the numerator and denominator. And then you could say 10/15 plus 9/15 equals 19/15. And I say, well, all right, that's fractions. I understand fractions, but not the rational expressions. Well, I want to go over it with fractions to kind of remind you of it's really the exact same thing, except now we're just dealing with polynomials. And remember, when we're adding and subtracting polynomials, we can only subtract polynomials that have the same variable factors, or a lot of times what we call combining like terms. So for instance, let's look at an example here. Let's say I have 3x squared over, let's say 2x, or let's do this. Let's do 2y divided by 3x squared plus 5 plus y squared divided by 3x squared. Now, since these have the same denominator, I can combine them. But when I look at my numerators, I notice that that is a 5, which is a number. This is a y, which has a variable factor of y to the first power. And this has a variable factor of y to the second power. So therefore, they don't have the same variable factors. So therefore, my final answer would just be y squared plus 2y plus 5 divided by 3x squared. Now, the next thing you want to do is after you've combined them, is always to look and see, how can you simplify them any further that would kind of help you simplify the solution. Or a lot of times, we also look into if it's possible to try to simplify even before you might add or subtract them. So let's go and look at one, at least one more that's going to have a binomial to it, or a monomial that you can go and do when we have not the same denominators. So let's go and look at let's go and talk about x plus 1 minus 2 over x plus 2. Again, I'm just making up really a problem for us to be able to work on. But I want to show you exactly what we're going to do in this case. Now, again, as I mentioned, as you're combining these, you're going to want to go and simplify at the end. But before we can even combine these, unlike this expression, we don't have any common terms. So to do that, I need to determine my LCD. In this case, my LCD is going to be x plus 1 times x plus 2. So therefore, I need to multiply to get both denominators to have that LCD. So I'll multiply by x plus 2 over x plus 2. And here I'll multiply by x plus 1 times x plus 1. All right? So now what I can do is now my common denominators, I can simplify these, but I can also simplify my numerators by applying distributive property. So applying distributive property, applying FOIL, those are going to be a lot of things that you're going to be applying, and especially factoring when doing these rational expressions. So therefore, I'll have 5x plus 2 minus 2x plus 2. Now I can apply the distributive property here and rewrite this as a negative 2x and minus 2. I like to do that when I'm simplifying this because what that helps me do is just say, all right, well now I can combine my like terms and say, all right, that's 5x minus 2x, and that's 2 minus 2, which is 0. So my final answer is 3x divided by x plus 2 times x plus 1. All right? So when we're going to be adding and subtracting, combining rational expressions, you're always going to want to look to get your denominators to be exactly the same, and then to simplify the numerators, and then simplify the whole expression as a whole. Thanks. When doing an example like this, basically, ladies and gentlemen, again, just like we did in the exact example, it's just like the last one, we need to find the LCD. Okay? Now, when we looked and found the LCD, 30 ended up being what the product of 5 and 6 was, correct? Yes? So if you take your two denominators and multiply them, you will obtain a common denominator, correct? However, that's not always the case. For instance, the common denominator of 9 and 2 is 18, right? You multiply them. However, the common denominator of 9 and 3 is not 27. The common denominator of 9 and 3 is actually 9, because 3 also divides into 9. Does that make sense? So you have to be careful. However, with polynomials, if you guys look at in this case, neither one of these divides into the other. So therefore, the common denominator is just simply going to be the product. So when we say the LCD, that's going to be x plus 1 times x plus 2. Now, just like I did with the numbers, I'm going to get common denominators. So to get x plus 1 to be x plus 1 times x plus 2, I have to multiply by?
2. I had no one to do.
What do I need to multiply by to get it to there?
I have all that.
Well, not all of it. What?
X plus 2.
Thank you. Very good. Thank you. X plus 2 over x plus 2. Over here, then I'd have to multiply it by everybody follow me? OK. So now, you guys can see, I can put parentheses around here. So now what I basically have is, now you guys can see I can apply distributive property here, right? So I have 5x plus 10 all over x plus 2 times x plus 1. And then over here, I can distribute the negative 3. Make sure you guys make sure you guys understand that's a negative 3, though. 5 minus 4. Please understand, guys, 5 plus or 5 minus 4 is the same thing as 5 plus negative 4, correct? You guys agree with me? Yeah. So what I'm actually going to do, anytime I'm doing subtraction, I am going to change this to an addition problem and make it now subtraction, or make it an addition problem with a negative number. That just helps me when I apply distributive property. So it's negative 3 times x, which is a negative 3x, and negative 3 times 1, which is a negative 3. Therefore, now I have x plus 2 times x plus 1. So what I want you guys to understand and see here is now I'm adding two fractions with the same denominator. And when you add two fractions with the same denominator, you keep the denominator, but you just add the terms in the new numerator. So I'm going to say 5x minus 3x and 10x minus 3. So 5x minus 3x is 2x. 10 minus 3 is going to be plus 7. And that's all over our common denominator, x plus 2 times x plus 1.
Wait, how did you just do that to my point?
Of what is adding fractions with unlike denominators compared to adding rational expressions with unlike denominators. So basically, when you guys look at this, again, you guys can see we have two fractions here, and they do not have the same denominators. So again, what we're going to want to do is, first thing is identify the LCD. OK? Now, again, as I mentioned, the easiest way to form the LCD is to multiply your two denominators. However, I will caution you that's not always going to be the case. All right? However, when you have two denominators that are in simplified form, that more than likely is always going to be the case unless they're already in the same. But so basically what I would do here, since it's not very apparent on what they share, the common denominator that they're both going to share is going to be their product, which would be x plus 1 times x minus 8. So the LCD is simply their product, just like the LCD was 21, 3 times 7. OK? Again, it's not always going to be that case, but very often it will. And we're going to do an example next time where it won't. So if here's my LCD, now I need to determine how do I get x minus 8 to be x plus 1 times x minus 8. What would I need to multiply x minus 8 by?
9.
X plus 1. And whatever I do in the denominator, I have to do in the numerator. Over here, I have x plus 1 in my denominator. To, again, determine to get this to my common denominator, I need to multiply it by x minus 8. So now, what you guys can see is now I need to simplify my numerators. So to simplify my numerators, I need to apply distributive property. OK? Now, you could multiply this out, but I'm just going to leave this as a product down below. So what I have here then is negative 2x plus positive 16 all over x minus 8 times x plus 1 plus 9x plus 9 all over x minus 8 times x plus 1. OK? So what I'd like you guys to see now is you see that we have now two fractions with the same denominator. So when we have two fractions with the same denominator, we just combine the terms in the numerator. So I'm just going to combine 9x and negative 2x, 16, and 9. OK? So this becomes 7x plus 25 all over x minus 8 times x plus 1. Yeah, I mean, you could multiply through the denominator if you want to. I just prefer a lot of times just to leave it and multiply it out.
Okay, so we have x minus 1 divided by x squared minus x minus 6 minus 4 divided by 5x plus 10. So just like we did before, we know we cannot subtract fractions. These are just two fractions, right? Or what we call rational expressions. But they're fractions in general. We cannot subtract them unless we have common denominators, right? Now, are these common denominators? Now, is there something that you guys know off the top of your head that you can multiply this by to get that?
5.
Well, what you could do is you could obviously always multiply the other expression by the other expression, right? That would work. But a lot of times that's going to be a little bit more work that we need to deal with. What I would recommend, ladies and gentlemen, when looking at this, is let's simplify these, right? Can we break these down? Can we break these down?
Yeah.
Of course we can. So let's break them down. So let's do 5x. It's a horrible act. 5x plus 10, and let's do x squared minus x minus 6. So can we simplify 5x plus 10? Of course, we can factor out a 5. How about this one? This is a trinomial, right? Remember, we have to get really good at factoring trinomials. So we know that this one is x minus 3, x plus 2. Good. Now let's rewrite it. So we have x minus 1 over x minus 3 times x plus 2 minus 4 divided by 5 times x plus 2. Now do you guys notice that they actually share something, right? So that means I don't have to always multiply the other two denominators by each other. So now what I'm going to do is write out my LCM. Because when adding and subtracting fractions, I want to find out what is the LCM. So what is it that they both have to share? What is the smallest value that they both have to share? Well, they both have to share the x plus 2. Then, they both have to share, what else do they have to share?
X minus 3.
They have to both share an x minus 3 and a 5. So now, I'm going to use that information. That's their LCM. That's what they both have to have in the denominator for me to combine them. So now, what I need to do is say, all right, here's what I have in this denominator. I need to get this to that least common multiple. So what do I need to multiply this fraction by to get that LCM there? 5 over 5. Very good. So I multiply by 5 over 5. Then I have this fraction. What do I need to multiply this fraction by just so I have a denominator that contains my least common multiple? X minus 3. Everybody follow? Now, we just multiply our numerators and combine our denominators. So therefore, I have 5x minus 1 minus 4 times x minus 3 divided by, I can now combine my denominators into 1, which is 5 times x minus 3 times x plus 2. Now, I distribute. I get 5x minus 5 minus 4x plus 12 divided by 5 times x minus 3 times x plus 2. And then can I simplify that one more time? Sure, I can do 5x minus 4x, which is x, and negative 5 plus 7, or negative 5 plus 12 is going to give me a positive 7. So therefore I have my final answer is x plus 7 divided by 5 times x minus 3 times x plus 2.
This is easier than the one.
I don't know. Do you think?
I think so.
Okay. Got it? All right. So in this problem, ladies and gentlemen, I have 5 divided by 6x minus 18 minus x minus 1 divided by 4x squared minus 14x plus 6. All right. Now, remember, we have to have the exact same variable factors, right? We have to have the exact same variable factors.
C.
I'm sorry. We have to have at least the common denominators.
Do these denominators look exactly the same?
No.
Right? And they don't even look anywhere close to being exactly the same. All right? Now, however, though, I'll give you guys a little hint. All right? If they're going to ask us to subtract them, more than likely you can say that they're probably going to be a factor of one another. Meaning that this is probably a factor of the other one. It doesn't have to be, but for the sake of saving you a lot of time, let's assume that it's a factor and see if we can find out what the other factor is. So anyways, I'm going to want to factor this out, because if I can write it as a product of its factors, it'll make a little bit more sense. So just like when we did multiplying and dividing, if you have polynomials or binomials, let's factor them out, right? So here I have 4x squared minus 14x plus 6. So now what we're going to have to do is factor that out. So let's see if we can factor it out. And when we factor it out, let's assume 6x minus 18 is a factor. Or let's not assume that it's a factor right now. Because actually it's not. Well, actually let's assume, and I'll show you what I mean. Okay, could 6x minus 18 be a factor?
No.
It could, but that means your other factors going to have to be a very fraction, small number, because you have to multiply 18 times something to give you 6, right? Yes? Okay. Now,
Good job, Ryan.
however, I could simplify this. Can I factor out a 6x minus 18?
Yep, it can be 6x times.
So I could use an x minus 3. So that could be a possible factor. But if I was going to factor this, what would be the first thing I'd want to do? Factor out the CEF. GCF, greatest common factor. So if I factor out a 2, I'm left with 2x squared minus 7x plus 3. Yes? No?
Sure.
Okay. So now what I can do is say, what two numbers multiply to give me positive 3. So if I know this is 2x, then I know that this has to be 2x, and this has to be x. So now I need to figure out what two numbers multiply to give me 3. It's either plus 3 and 1 or negative 3 and negative 1, right? But since I know, ladies and gentlemen, that this is a negative middle term, I know the two factors have to be negative 3 and negative 1, right? Yes. And if I multiply 2, to get to 7, I'm going to have to multiply 2 times 3. So that means this is going to have to be x minus 3, and that would have to be x minus 1. Because if I swap those, 2 times negative 1 would give you negative 2, and x times negative 3 would give you negative 3. That would give me negative 5, but I need negative 7. So therefore, I can get to it. And FYI, do you guys notice there's that factor there? X minus 3, right? Yeah, same factor. So now let's rewrite this in factored form. So I have 5 over 6 times x minus 3 minus x minus 1 over 2 times 2x minus 1 times x minus 3.
Yeah. Hoorah.
Now we have it written in our factored form, okay? And as you guys can see this, now what we want to do is start writing out our LCM. So, least common multiple for our denominator. So what do they share? They both share in what?
3.
X minus 3. Alright, but what about, let's look at the numbers. What is the largest number that both 6 and 2 divide into? 6. Actually, I should have wrote that first. Alright, then what else do they have that maybe they share or they don't share? Well, 2x minus 1, right? So what do I need to multiply over here to get it to be 2x minus 1? 2x minus 1. So the LCM is 2x minus 1. Therefore, all I need to do is I need to make sure I multiply to get both denominators to be 6 times x minus 3 times 2x minus 1. So let's work on the left side here real quick. So on the left side, I have 6 times x minus 3, but what do I need to multiply then to make it look like my LCM? 2x minus 1. And remember, you need to multiply on the top and bottom.
So what does that mean?
Schmuck.
6.
Flop.
What does that mean for x?
We'll talk about that in a second. Then, over here,
You're gonna get 3.
over here, what I'm going to have is I need to multiply. So I already have the 2x minus 1. I already have the x minus 3, but I need to get the 2 to be 6, so I need to multiply by a 3. Okay, so now let's simplify our numerator and then see what and then our denominator is going to be our least common multiple. So therefore, we'll have 5 times 2x minus 1 minus 3 times x minus 1 divided by 6 2x minus 1 times x minus 3. Yes? No? No? Yes? Okay. So now, let's go ahead and simplify this. Simplify the numerator again, and you get 7x plus 2 over 6 times 2x minus 1 times x minus 3. Yes, it's minus 3. Okay, anybody have any questions on this? No, sir? Good? Divided by y squared minus 3y minus 10 plus y divided by y squared plus y minus 2. All right, now before, ladies and gentlemen, it was pretty basic to find if I had 1/4 plus 3, 6. We already knew our LCM in this case, right? We knew the LCM is going to equal 12. That one's pretty basic, right? And even when we added a squared and a to the 5th, you could say, all right, well, the LCM is a to the 5th. It's pretty basic when you just have numbers and variables that are multiplied by each other, right? You just say, you pretty much just take what is the largest number that you multiply to get your numbers, that's part of your LCM. And what is the largest exponent, and that's your LCM. That's part of your LCM, right? So, but now we're coming to a problem where we have a trinomial and another trinomial. So we could, to find the LCM, we could say, that's part of your LCM and that's part of your LCM and multiply them. Or that might reduce some redundancy because the LCM in this case is 12. But you could also say a common multiple would also be, you could look at 24, right? If you multiply them, it would be 24. But that's not the least common multiple. We always want to use the least common multiple so you don't have to simplify at a later time. So what I'm going to do is I want to see, can I factor these out? All right, whenever you guys see a trinomial or even a binomial, see if you can look and work on some factoring. So we look at this and we say y squared minus 3y minus 10. Can that be factored? Of course it can. Y minus 5 times y plus 2. And then we see, can we factor y squared plus y minus 2? And can that be factored? Of course, y plus 2, y minus 1. Yes? No? That's right. OK. So now what I'm going to do is I'm going to rewrite this as y minus 5 over my new factored form, y minus 5 times y plus 2 plus y over y plus 2 times y minus 1. OK. So now, as I go and write my LCM, so now I wrote it down and I factored each term. So now when I go and write my LCM, what does my LCM have to contain? Well, what is the common multiple between these two that they both have to contain? Now they're both going to have to, if I was like going to multiply these out, do I need to show y plus 2 twice, or can I just show it once? Does y plus 2 both divide into y plus 2? Yes. So I can write my LCM is going to be y plus 2. And then what else needs to be a part of my LCM? Y minus 5 and y minus 1. So ladies and gentlemen, my LCM is, you could see, if I were to multiply both of these by each other, I would have a redundancy of y plus 2. But now when I factor them out, I notice that my LCM needs to only contain y plus 2, y minus 1, and y minus 5. So now I need to look at it and say, what do I need to multiply each term by to get it to that LCM? So over here, to get this to my LCM, I need to multiply by y minus 5, right? And I multiply that on the top and the bottom. Over here, to get it to my LCM, I need to multiply by y minus 1. Does everybody follow me with this? OK, so now, since I'm going to multiply them, I have a binomial times a binomial. That means you're going to have FOIL. And then over here, I have a monomial times a binomial, meaning I'm going to have to apply distributive property. So I'm going to do a little work in my head. Y times y, y squared. Y times negative 5 is negative 5y. Y times negative 1 is negative 1, so that becomes a negative 6y. Negative 1 times negative 5 is a positive 5. Plus y times y is y squared minus 5y. So I just simplified. I just multiplied these out. And then I take them over my LCM, or common denominator. OK, now, to get my final answer, let's just combine our like terms. So we could say y squared plus y squared is 2y squared minus 11y plus 5 over y minus 1 times y minus 5 times y plus 2. Now, we're not done yet. Usually you guys say, oh, this looks like we're pretty much done, right? But is this something that can be factored? Could be, right? Let's just go and check it. What two numbers could I multiply that would give me a negative 5 and a negative 1? And guess what, ladies and gentlemen? This actually can be factored. 2y squared minus 11y plus 5. By practicing my factoring, I could say this is 2y minus 1 times y minus 1. Would you guys agree with me on that? Let's check it. 2y times y is y squared. 2y times, no, sorry, that's 5. I said it, but I didn't write it. 2y times y is 2y squared. 2y times negative 5 is negative 10y. Y times negative 1 is negative 1y, which add up to give you negative 11y. And negative 1 times negative 5 is positive 5. So if you wrote it here, guys, you're very, very close. All right? However, we just need to understand, though, we can factor this one more time, which would give us 2y minus 1 times y minus 5 over y minus 1 times y minus 5 times y plus 2, which is important in this case because now the y minus 5s cancel out. So the final answer is going to be 2y minus 1 over y minus 1 times y plus 2. It's a long problem, has a lot of steps, but you need to make sure you can follow through and get everything. Does anybody have any questions on that? But that's how you would finalize that problem. OK. Here's what we have, ladies and gentlemen, is we have 2a divided by a minus 3 minus 2a divided by a plus 3 plus 36 divided by a squared minus 9. Now, what we talked about, Juliana, last class period was adding and subtracting rational expressions. All right? And when we added rational expressions, we had to make sure that they had the same denominator. Now, if it wasn't overly apparent what the common denominator was, we had to make sure we could factor. Well, we know that these are both binomials that we can't factor down further. But we do have another binomial that we could factor. So I write this down as a squared minus 9. I say, all right, how can I factor that down further? But I know that this is a difference of two squares. So Alex, if you want to move back on the other seat if you need, we can factor this down to a minus 3 times a plus 3. Because we've been doing a lot of factoring practice, right? Yeah. So we're very, very familiar with the difference of two squares. So I'm going to rewrite this as a minus 3 times a plus 3. And the reason why I'm going to rewrite it is because now what that's going to allow me to do is visualize and see out of all three of these rational expressions, what has to be my common denominator or my LCM. So I always like to write in my LCM. And the LCM, the least common multiple of all my denominators, is going to be, that means the factor that they all have to contain would be, yes, I heard it, a minus 3 times a plus 3. That means for me to add or subtract every single one of these rational expressions, they all have to have a denominator of a minus 3 times a plus 3. Okay? So if I look at this last expression, does this already have the common denominator? Yes. So do I need to multiply by anything? No. However, this middle term, though, do I have it as a common denominator? No. So my denominator is a plus 3. I need to get it be multiplied by a minus 3. So what I'll do is in purple, I'll multiply it by a minus 3. Now remember, to keep equivalent equations, or fractions, we have to make sure we multiply on the top and the bottom. Then I look over here, and I have a minus 3. However, to get the LCM, the common denominator, I need to multiply it by a plus 3. OK? So does everybody see what I did and why I did it? Yes? No? Maybe so? OK. So now the next thing I'm going to do is just distribute. Now, we know that by adding and subtracting, my numerator is all going to be the same. Or I'm sorry, my denominator is all going to be the same. But now I'm going to have to apply some operations up top. So before we do that, let's just go ahead and apply distributive property, because we have some monomials times some binomials. So when I distribute, I get 2a squared plus 6a minus 2a squared minus 6a plus 36. And remember, this is all over our LCM, or our common denominator, of a minus 3 times a plus 3. OK, so all I did is I pretty much took each rational expression, the numerator, and put them all together. All right. So now what I can do is now I need to apply distributive property here again, because remember, it's minus this term. Oh, actually, did I already do that? No. So now we need to apply distributive property here, because I just multiplied the 2a, but I didn't multiply the negative. So let's go and reduce this one more time. So I'll do 2a squared plus 6a minus a 2a squared plus 6a plus 36. It is 2a minus 3 is minus 6a, but now I'm distributing the negative sign, so it turns to a positive. And then we rewrite it. So I have a minus 3 times a plus 3. And I'm doing a lot of steps, one thing. And now we just combine our like terms. So we combined the a squareds with the a squareds, the a's with the a's, and then we have our constant. So 2a squared minus 2a squared is 0a squared. 6a plus 6a is 12a plus 36, all divided by a minus 3 times a plus 3. OK? And then what we could always do is see if we could factor our 12a, right? We notice these have a common factor. So if I factor out a 12, so let's go this way. If I factor out a 12, well, I'll be left with a, and then 12 goes in there, what? Plus 3? All over a minus 3 times a plus 3. And since we're all multiplying these terms, these are going to divide out to 1. So I'm leaving me with my final answer of 12 divided by a minus 3. OK? That's your final solution. OK. So if you guys need to graph this, you can always use your graphing calculator. And you can also always go back to a table of values, right? There's nothing wrong with it, everything else. However, ladies and gentlemen, we practice using things with the transformations to help us out. So let's just go, whenever we're doing transformations, there's a couple important things we need to make sure we understand. First of all, we need to know what the parent graph looks like, right? You can't transform something that you don't know what you're transforming from. So we first graph the parent graph. OK? Now we look at our transformation and say, all right, what's happening? Right? We now have a equals 2, h equals 4, and k equals 2. Right? Remember, it's a opposite of h, so h equals 4. So what does that tell us? Well, a is going to tell us we're going to have a stretch. right? Or I'm sorry, compression, or it's going to be stretched vertically, compressed horizontally. Either way, but we'll show you guys how to evaluate for that. Then the next thing, H is going to tell us we're going to shift right 4, and K tells us we're going to shift up 2. Now, here's the way I like to do it. You guys know we have asymptotes right now that are along the x-axis and along the y-axis, right? We know that's where they exist here. I'm sorry, I probably should have written it here. So if I'm going to be shifting, notice that my asymptotes intersect at the origin. If now I'm taking this graph and I'm shifting it to the right 4, that means this vertical asymptote is going to shift how far? 4 over. So now I can say 1, 2, 3, 4. So now I'm going to have my vertical asymptote is going to be at x equals 4. And then I have my k tells me I have to shift my graph up 2. Okay, so you guys see how I can apply the transformation by using my asymptotes? All right. Now, you could just say, oh, well, let's just estimate in the right like that. What I want you guys to do when you guys are doing a problem like this is let's just, to keep it simple, a lot of you guys are going to want to put your graphing calculator, plug it in there, and try to throw up a graph. That's fine. But just like when we did quadratics, you guys, I want you to evaluate at least 2 points on either side of our asymptote. For a quadratic, I told you to evaluate at least 2 points on either side of the axis of symmetry. For hyperbola, that's the exact same thing. I want you to evaluate at least 2 points to the left and to the right. All right? Asymptotes. So right now, we kind of know what the shape of the graph is, but we have a stretch of 2. So I want to see how that's going to affect the graph. So I'm going to pick some kind of simple points. And usually, ladies and gentlemen, to help you out, it's usually best if you pick, just like for quadratic, you don't want to pick points that are really far away, right? For a quadratic, you want to keep them very simple, very close. So I'm going to pick these 2 points, and then I'll pick 5 and 6 over here. So let's go ahead and do f of 2. So f of 2 equals 2 divided by 2 minus 4 plus 2. 2 minus 4 is negative 2. 2 divided by negative 2 equals negative 1 plus 2, which equals 1. So at 2, I go up 1.
Wait. 2 on the regular graph? 2 on the never mind.
OK. Now let's do f of 3. So now I do 2 over 3 minus 4 plus 2. 3 minus 4 is negative 1. 2 divided by negative 1 is negative 2. Wait a minute. Why did I shift up 3? What's wrong? Oh, OK. So therefore, that equals 0. So at negative 3, I'm at 0. OK? Now, understanding the shape of this graph, we know that the graph is going to go through these 2 points. And the important thing, guys, remember asymptotes. Asymptotes where a graph approaches. So we know these 2 points are going to now approach that asymptote. And they have to now approach this asymptote. Right? Yes?
And then if you do 5, it'll change to 4.
Yep. Then I do 5. So I'll do f of 5, which equals 2 over 5 minus 4 plus 2. Which equals 2 over 1 plus 2, which equals 4. So at 5, I have 1, 2, 3, 4. And then let's do f of 6. 2 over 6 minus 4 plus 2. So that becomes 2. 1, that becomes what? 3. So at 6, I get 3. And then again, you have these 2 points. We know they have to fall into this shape where they're going to approach both asymptotes. And there you go. I have now graphed it. Does that make sense? OK, but we're not done yet. Because now we need to still go and determine, now we need to say what are our new asymptotes and what are our domain and range. So we look at this and say, all right, our new asymptote is now at 1, 2, 3, 4. And our vertical asymptote is at, so our asymptotes, we have a vertical asymptote at x equals 4, right? It's written as a equation for a line. And also we have an asymptote at y equals 2. Now let's determine the domain and range. So the domain, we don't have any restrictions except for one value we cannot plug into our function, which would be at
0.
well, what happens if we put in 0? If I put 0, 0 minus -4 is -4. 2 divided by -4 is -1/2. So yeah, we actually can evaluate for 0. What value can I not put in for x? Destin, what value can I not put in for x?
No idea.
OK, that's exactly why you need to be looking up here. Yes? What value?
4.
Exactly, 4. If you put in a 4, then you get 0, which we know, right? So our domain is going to be all real numbers, except x cannot equal 4. OK? Now let's look at the range. The range, we don't have any restrictions on our range except for what value? 2. So our range is going to be all real numbers, except y cannot equal 2. Dimitri, you got that? OK.
So all real numbers, you can just write it on.
Yes. All right. So ladies and gentlemen, if I was going to say, hey, graph this, we're only going to do a couple examples, all right, for your homework and for a test. But let's say I ask you, what does this graph look like? You need to have an idea. And obviously, yes, you can go and plug it into your graphing calculator. But what if you don't have a graphing calculator? And what if you're on a test and they're just asking you something where they want you to know the shape? We talked about you can always apply table of values, right? Always. But table of values kind of takes a little bit of time, doesn't it? It's a good way to understand it, but it takes a little time. So what we're going to use is we're going to use our transformations to help us graph this problem, all right? So here's what I got. Remember, I told you guys the general transformation form we had was a times 1 over x minus h plus k. All right? And remember, when going back to transformations, a tells us if there's going to be a reflection, right? And if we're going to have a stretch or a compression. And our h shifts it left and right, and k shifts it up and down. So before we do our transformations, the only way you're going to be able to know how to do transformations is you first have to know what the parent graph looks like, right? You can't graph something by using its transformations if you don't know what to transform it from. So that's why you have to know the parent graph. And that's why I went through that parent graph with you guys. All right, so now we know what the parent graph is. But remember, this parent graph has asymptotes, where the graph approaches. Now, I like using the asymptotes to help me with my transformations. The reason being is this hyperbola, as we call it, is kind of difficult, right? To kind of shift around. It's like, what is the shape of this thing? But yeah, that's the name of it. But what we do know about the hyperbola, which is cool, is that the hyperbola approaches its asymptotes. So if I look at this graph, ladies and gentlemen, and I look at my transformations.
Are they never going to simplify?
No. So I look at my transformations. And what I notice is, if I have x minus h, here I have x plus 1. That tells me I'm going to shift my graph where?
Over right.
Remember, it's opposite of h. H tells you to go left or right, so it's
To the right.
left 1, right? Well, rather than trying to shift the hyperbolas, let's shift our asymptote, right? Because if our graph is going to shift to left, that means I'm now going to have a vertical asymptote at x equals -1.
Yeah, I think that I remember sure.
I'm just going to try to finish this up, OK? And then we'll go through some points. So the next thing is now we look at the -4. -4 tells you to shift the graph down 4, right? So I'm going to go down 4 units, 1, 2, 3, 4. And now,
Are we supposed to make our graph dotted?
your asymptotes we represent as dotted lines, OK? Those are going to be the lines that your graph is going to approach, all right? Now, we need to go back, and now we look at our a, right? I'm multiplying a because a times 1 is a. So you guys can see that my a is equal to -3. So when it's negative, that tells you what's going to happen. When it's negative, that means it's going to reflect over the x-axis. So what that means is now this graph is being reflected over the x-axis, right? So I'm going to have something that's going to look like that and like that. Rather than it taking this shape, it's now being reflected over the axis. Now, we don't know what this exact values are going to be. So, ladies and gentlemen, what you're going to have to do for your test, all right, is to kind of show me that you know at least some values. I'm happy that some of you have a graphing calculator where you can graph it and get the idea of what the graph looks like. That's awesome. However, just by plotting what the graph looks like is not going to be able to get you the credit. What you're going to have to do is show me a couple points, and I'll explain it. If you guys remember, when you guys took your test on quadratics, what I asked you to do was define the axis of symmetry and then pick 2 points to the left and to the right. I said don't go very far from the axis of symmetry because the quadratic gets very large or very small very quickly, right? So you wanted to pick points that were very close to the vertex or the axis of symmetry. The same thing is going to be the case for my asymptotes. Don't pick numbers that are very far away from your vertical asymptote. So we know my vertical asymptote is at x equals -1. So when I do my table of values, I'm going to do 2 points to the left of the vertical asymptote and 2 points to the right. So since x is equal to -2, I'll do -2 and -3. And then I'll do 0 and 1.
I have a question.
Yes?
When is the asymptote going to be positive? You said it's -1. Is it always going to be -1?
If it was x minus 1, I'd shift my graph to the right, and the asymptote would be positive. OK? It would be in the positive x value. Yes?
The parent graph, is it the only one I can never intersect at 0, or is the...
Yeah. So this is just the parent. At the parent graph, we can't intersect at 0. And I'll explain a little bit once we get to our points, OK? So now let's evaluate for our points. So I do f of -2. You plug -2 in for x, right? So we have -2 plus 1 is -1. -3 divided by -1 is 3. 3 minus 4 is -1. Now let's do -3. So I'll do f of -3 equals -3 divided by -3 plus 1. Well, -3 plus 1 is -2. -3 divided by -2 is a positive 3/2. Minus 4 is going to be 2.5. Oh, minus 2.5? Yes? No? Roughly, I'm just keeping a decimal to keep it up there. Now, let's go and look at f of 0. Now, some of you might say, well, Mr. McLogan, you said x cannot equal 0. And that's true when we had our parent graph or when we have a function where 0 cannot be on the bottom. But if I plug in 0 for my x, do I have 0 as the denominator? No. I don't have 0 as the denominator. Because 0 plus 1 is 1. 1 divided by -3 is -3. -3 divided by -4 is -7. OK? Now we look at f of 1. f of 1, I just take -3 divided by 1 plus 1 minus 4. And then here, I'm going to have 2. So this one equals -3/2 minus 4, which will be a -5.5. And I'll just get out of the fractions, do the decimals to help you guys out as far as graphing goes. So now let's plot our 4 points. Oh, sorry, let's write these down there. So this is -2.5. This is 0 is -7. And at 1, we have -5.5. So let's plot the points. -2, -1. At -3, we have -2.5. Let's go and take a look at 0. At 0, I have -7. 1, 2, 3, 4, 5, 6, 7. And at 1, I have -5.5. 1, 2, 3, 4, 5. So what you guys can see is the actual shape. So remember, the graph has to go through these 2 points and then approach each asymptote. So the actual shape of the graph is going to look like that. Yes? OK. So remember, here's my asymptotes. Are right now at x equals 0 and x equals y, right? Or 0 equals x and 0 equals y. Since I shifted it horizontally to the left, I just moved the asymptote over to the left. And then since I shifted it down 4, I just moved the vertical or the horizontal asymptote down 4. All right? The other important thing for you guys to notice about this is, does this make sense for a horizontal asymptote to be at negative 1? What happens when I put -1 in for x? You get 0, right? Which we know is undefined. So that's why we know this vertical asymptote is undefined. OK? That's it. So remember, when identifying the asymptotes are what we call non-removable discontinuities, right? We talked about asymptotes and holes last class period. Asymptotes are non-removable discontinuities, where holes are removable discontinuities. So even though we know our discontinuities is what's going to make our denominator equal to 0, we want to be careful in making sure that it's not a hole or a asymptote. So what we can do then is factor our numerator and our denominator. So if I factor our numerator, if I factor out my numerator, I factor out a 2, I'm left with x minus 4. And if I factor out my denominator, I'm left with a x minus 4 times x plus 4. That's really, really important, because now you can see that the x plus 4s divide out. Since those divide out, they're not an asymptote. They're still a discontinuity, but it's not an asymptote. It's now called a hole. So anyways, to find the vertical asymptote, I'm only going to take this discontinuity and set it equal to 0. So the only asymptote that occurs is at -4. X minus 4 equals 0. X equals 4 is still a discontinuity, but it's a hole. OK? So based on the question, if I said, hey, what's all the discontinuities, you'd say, oh, it's 4 and -4. But that's a hole, but that's an asymptote. I'm just asking for the asymptote. So that's why I like this problem, because it gives you a hole, like your homework, or like the work that we did. To find the horizontal asymptote, again, we compare the degree in the numerator compared to the degree in the denominator. Remember, whenever the degree in the denominator is greater than the degree in the numerator, y equals 0 is your horizontal asymptote. Done.
All right, what I'd like to do is show you guys how to find the vertical and horizontal asymptotes. Remember, what an asymptote is as our graph is approaching a certain number, it's going to keep on approaching that line, but it's never actually going to go ahead and get to that point. So on a graph, it's going to keep on, as our values keep on getting larger, it's going to keep on getting closer to the line, but it's as what we also like to call it, just go ahead and approaches affinity. So what I want to do here is, if I want to find the vertical asymptote, for both these equations, what I need to do is I need to set both my denominators to 0. So I just say 0 is equal to x minus 2 cubed. Okay? And then here I get 0 equals x squared plus 1. So when I go ahead and do this, I go and factor this, I get x equals 2. Okay, I take a cube root on both sides. You guys need me to show that? We okay with that? Take a cube root. I'll just show it. Cube root on both sides to get rid of the cubed. Okay, therefore then you have 0 is equal to x minus 2. Add a 2 on both sides. X is equal to 2. Okay? Over here, I noticed that there is no number that's going to be an imaginary number, right? That's going to be I, square root we're on, equals x. Right? We worked on taking the I, because that's going to be negative. You take the over, it's going to be square root of -1. So therefore, there is no there's no x-intercepts or vertical asymptotes for here. Then for the horizontal, so that's your vertical. And for here, vertical, we have none. I don't know why I did the double E. And now to go ahead and find the horizontal asymptote. Remember the horizontal asymptote, what we need to do is we need to look at your exponents of your leading coefficient. And if we have if our degrees of here is what we look at, and here you can pretty much write we have x to the 0, right? Because there's nothing written there, so it's x to 0. So if you guys remember what we wrote down last class period is when you go ahead and compare this, eventually if I FOIL this all out, I'm going to get x cubed, right? So essentially what I have is my $2 x over x cubed. And if you guys remember that whenever your the degree in the numerator was less than a degree in the denominator, therefore you had a horizontal asymptote of 0. So therefore, your vertical equals this, horizontal equals y equals 0. All right? And then for number 12, now we notice that we have x squared is equal to x squared, right? So we have, when I'm looking at my leading coefficients, now these are equal to each other. So when they're equal to each other, we have A and B is what we call their coefficients of them. And what to do is when you have 2 is equal to 2, when you have their degrees are equal to each other, then the horizontal asymptote is the ratio of A over B. So the horizontal for this problem is going to be 3 over 1, because the coefficient for this problem is 1. So it'd be 3 over 1. So that's how you find the vertical and horizontal asymptotes of given functions.
Well, let me show you. If I wanted to find the x and y intercepts, to find the x-intercept, all right, if you guys just remember and visualize the graph, x-intercept is where it crosses the x-axis. That means your output value, or your y value, is equal to 0. So I plug in 0 in for my f of x. 0 equals x squared over x squared plus 9. Now, since this is on the bottom of my fraction, it's my denominator, to get rid of this, I need to multiply by that number. So I multiply by that number on both sides. Well, x squared plus 9 divided by x squared plus 9, these are going to cancel out to leave me 1. So therefore, this times 0 gives me 0, so I'm left with 0 equals x squared. Take the square root, 0 equals x. So the x-intercept, or my x-intercept is going to be at 0. 0. To find the y-intercept. Now, the y-intercept is when my x value equals 0. So you're going to plug in 0 in for x. So I say f of x equals 0 squared all over 0 squared plus 9. Right? And what you guys will notice is this becomes 0 over 9. Well, 0 divided by anything is going to give you 0. So here we have f of x equals 0. So for this problem, my x-intercept is 0, my y-intercept is 0. So my intercept is just going to become 0, 0. All right. Now the next thing they asked for this problem was to find the domain and to go ahead and find the vertical. I'm sorry, not the domain, but the vertical asymptote and the vertical asymptote and horizontal asymptote. So remember, to find the vertical asymptote, what we need to do is we need to set our denominator equal to 0. So I say x squared plus 9 equals 0. And this is for your vertical asymptote. So to solve for this, the next one, I subtract the 9. And when I take the square root, I have x equals the square root of negative 9. You cannot take the square root of a negative number, right? That's going to give us into actually an imaginary asymptote. So therefore, there's not going to be a vertical asymptote. Since it's going to be an imaginary or a complex number, there is no vertical asymptote. When looking for the horizontal asymptote, what we need to do is we need to look at their degrees. And since their degrees are equal to each other, what we do is we take the coefficient of each value and we divide them. So this would be 1 over 1, which is equal to 1. So therefore, we can say the horizontal asymptote is going to be equal to 1. Any questions on what? Yes?
Did we have to do that little graph in there?
No. I just wanted to kind of visually show you. So the horizontal asymptote is at 1. That means this graph, like let's say it's right there, there's going to be this little dotted line that's going on that my graph is never going to touch. All right, and we do know also that it intersects right there. So the only thing we know is my graph is going to intersect right there, and it's never going to touch that line. That's all we know for right now. All right, ladies and gentlemen, what I want to do is show you how to find, we're just going to work with the vertical and horizontal asymptotes, all right? After that, we'll show you what to do for the remaining part. So to find the vertical and horizontal asymptotes, we need to go back and look at our notes and remember our rules. Okay, Rebecca? So I'm going to get to this here. First one is to find your vertical asymptotes. Remember, ladies and gentlemen, we talked about the domain is all real numbers except when our denominator is equal to 0. This is pretty easy to see when is our denominator going to be 0. It's when x equals -1, right? However, for more complicated problems, let's go through the process of what we want to do. So to find the vertical asymptotes, what you're going to do is you're going to take your denominator and you're going to set it equal to 0. All right? The reason why you want to set it equal to 0 because you want to find the values of x that make your equation equal to 0. So this one we can do in our head. However, let's just practice it so we know that x equals -1. All right? So your vertical asymptote. Yep. I'll show you. So your vertical asymptote is when x equals -1. That means your domain is going to be, I mean, we're not working with domain right now. We're not asking, but your domain is all real numbers except when x equals -1. And, you know, we can write that as from -infinity to -1 union -1, comma, infinity. All right, that would be your domain, FYI. All right, that means all from -infinity to infinity, which are all real numbers, except for our value -1. Okay, so now let's find the horizontal. Ladies and gentlemen, the horizontal asymptotes all deal with your degrees of your two polynomials, right? We talked about rational functions. Remember I said you have a polynomial. The rational functions we're going to talk about today have a polynomial up top and a polynomial on the bottom. So for each polynomial, we have a degree, right? We have a degree of every polynomial. Even a constant polynomial has a degree of 0 because it's x to the 0. So every polynomial has a degree. So I need to determine what are the degrees of my polynomial up top and my polynomial on the bottom. Well, to first do that, I want to make sure that my polynomial is written in descending order, correct? So let's rewrite this in descending order, right? Remember, you always have your highest degree first. So this should really be rewritten as 2x plus 5 over x plus 1. All right? Yes?
So when do you write it in descending
Always.
order?
Always want to write in, yeah, always want to take your polynomial to write it in descending order. Because this is my degree, right? You could say that, right, that would be x to the 0, because x to the 0, anything raised to the 0 is 1. 1 times 5 would just be 5, but we don't write it in there. So now I look at my two exponents. My two exponents are 1 and 1, right? So what we say, if you guys remember our formal definition, we had the exponents as n and m. In the notes, we represented the degree for the top polynomial is n, and the degree for the bottom polynomial is n, or is m. So whenever your degrees are equal to each other, m, 1 equals 1, or m, or n equals m, as we had in our notes, whenever they're equal to each other, the horizontal asymptote is equal to your leading coefficient divided by your other leading coefficient. So it's going to be 2 divided by 1. Okay, as 1 is going to be your leading coefficient for your denominator. So you take the leading coefficient of your numerator divided by your denominator, which is just equal to 2. Yes? That's it. That's all you guys got to do. So for horizontal, just determine whenever you have the same degree for top and bottom polynomials, you take their leading coefficients and you divide them. Yes?
So we're doing the horizontal, or no, the vertical, we're just supposed to set it equal to 0 and then solve them whenever we get it.
Exactly.
That's
Yep.
like,
All right, what I'd like to do is show you guys how to find the slant asymptotes. All right, I'm sorry, not just asymptote. Let's find the vertical, and let's find the horizontal, horizontal, and slant. Okay, so the first thing, I like to start with the vertical. And when finding the vertical asymptotes, all right, what we need to do is we need to find out what values are not going to be true for x, right? Because vertical, if you're going to think of like my graph here, vertical are going to be vertical lines. So we're going to have x values that our graph are going to approach, but they're never going to touch or ever going to cross. So therefore, we have to find certain x values that are not a part of our function. So when you're dealing with a rational function, we know that if we find values that make the bottom 0, those cannot be a part of our function because you cannot divide by 0. So to find those values that make our bottom polynomial 0, I need to set our bottom polynomial equal to 0. Then when I solve, I get 1 equals x squared. When I take the square root, I get x equals plus or minus 1. Therefore, I have two vertical asymptotes. And you know what? Let's do a little sketch graph here so we can see. So therefore, we're going to have -1 and at 1.
The next price, please report.
All right, those are two little asymptotes that my graph is never going to touch. It's just going to keep on approaching it. Keep on approaching it without bound, we like to say. When checking out my horizontal, there's 3 rules, and I'll try to say them as slowly as possible because I've made a couple videos on this and I don't want to write them down again. So if you want me to see what they're written down, check out some of my other videos on asymptotes. But for horizontal, we need to look at the degrees of your leading term. When I look at the degrees of the leading term, if your degree of your top term or top polynomial is less than your degree of your bottom polynomial, then your horizontal asymptote is when y equals 0. If these two degrees were equal to each other, then you need to take the coefficient of each of those leading terms and divide them, and that's what y would equal as your horizontal asymptote. In this case, though, when you have your degree on your polynomial is larger than a degree on the bottom polynomial, you do not have a horizontal asymptote. What you have is what we call a slant asymptote. And to find a slant asymptote, what we're going to have to do is we're going to have to use long division. And the reason why we want to use long division is because one thing, when we're doing synthetic division, remember it always had to be in the form of a factor, right? And you had to use that 0 to do this. Well, here we don't have a factor, we're not looking for factors or zeros. So long division is going to give us our quickest method and area to find our horizontal asymptote. So let's do long division. Remember, you take your first term, divide it into, I forgot here. When doing long division of this sort, we need to make sure every term is created. So I don't have a 0x, so I need to create one. Okay? Notice that my divisor is x squared minus 1. Well, to finish up this problem, I got to make sure that every single x term is represented when dividing. So x squared goes into x cubed, x times. X squared times x cubed, or x squared is x cubed. All right? X times 0x is still going to give me my 0x squared. And x times -1 is going to give me a negative 1x. Obviously, I have nothing left over here to bring down. So therefore, what you do is, so I'll have 0, right? So 0 minus, so that was cancel out. That's 0. 0 minus a negative 1 would give me a positive x. So I'll have x over x squared minus 1. So we're not concerned about the remainder, though. All right, we don't care about the remainder. All we're concerned about is what our divisor is without that remainder. So therefore, my horizontal asymptote is going to be this x line, which looks like that. So therefore, this is another line that my graph is going to approach, but it's not going to cross it, or it's not going to cross it, nor will it touch it. So without doing a table of values or without looking at graph calculator, we won't know what the graph looks like, but you can at least see where the graph is not going to touch and it will approach. And that's how you find your horizontal, slant, and vertical asymptotes. You don't do anything different. First thing you always want to do is the vertical asymptotes. And just because I think vertical asymptotes are the easiest. Factor, and then make sure you don't have any holes, and then just set the denominator equal to 0. However, is there anything that we can multiply to give us -7 that's going to add to give us -3? No, so that's not factorable. So I know obviously that's not going to divide out. So my vertical asymptote is just x plus 3 equals 0. So x equals -3. Done. Horizontal asymptote. Again, you're comparing the degrees. Actually, I like doing green with these. So guys, we already did this. We did when the degree is greater than the degree in the numerator, then y equals 0. When the degree is equal to the numerator, y equals a over b, which is leading coefficient over leading coefficient. Now we have an example of the degree in the denominator is less than the degree in the numerator. So there is not a horizontal asymptote in this case. But you guys need to make sure you can distinguish all of these. Okay? Know when they occur, know how to find them. But now, since we do not have a horizontal asymptote, we now have a slant asymptote. So how are we going to define the slant asymptote? Well, all we simply do, and the reason why slant asymptotes come, I think they're actually the easiest to remember, is because x plus 3 divides into that, right? This is a smaller degree than that. So what we can do is do long division. In this example, you actually could do synthetic division actually too, right? But majority of the problems a lot of times you have to do long division. So we're just going to practice long division. So again, let's go through long division step by step again. How many times does x divide into x squared? X times, because x times x gives you x squared. X times 3 gives you 3x. Then we subtract the rows. X squared minus x squared is 0. Negative 3x minus 3x. So if you owe me $3 and you borrow $3 more, you now owe me $6. So negative 6x. Now, how many times does x divide into negative 6x? Negative 6 times. Negative 6 times x is a negative 6x. Actually, let's do that green. Negative 6 times 3 is a negative 18. Bring down the negative 7. Subtract your rows. That becomes a plus, so that's 11. And that's your remainder. However, yes? How many times does x go into negative 6x? Negative 6 times. Then remember, you take that negative 6. I didn't. I did negative 3x minus 3x. Is negative 6x. Right. Now, it's really important for you guys to understand. Diana, close that. Really, really important for you guys to understand. Once you apply long division, your slant asymptote is your quotient, not dealing with your remainder. I don't want to mathematically get into it, but this goes to 0. Okay? So your slant asymptote is going to be y equals what the quotient is, which in this case is x minus 6. Okay? First example, ladies and gentlemen, is the vertical asymptotes, right? All right. Hopefully, we're going to be OK with vertical asymptotes. All you do is set your denominator equal to 0, right? Go ahead and factor. X minus 3 times x minus 2 equals 0. X equals 3. Oops, plus 2. X equals negative 2. Does everybody follow me? Everybody OK? OK. So when I'm going to graph this, though, we have to graph those asymptotes. Just that finding them is not really going to do us any good. So remember, guys, remember when we were talking about domain, right? The values that make the denominator equal to 0 were not a part of our domain. So our asymptotes are not a part of our graph. Our graph is not going to cross these asymptotes. So I have an asymptote at 1, 2, 3, and at -2. So to represent the asymptotes, we're going to use a dashed line. It's x equals, so that's a vertical line. Does that make sense? All right. For number 2, which is the horizontal asymptote. To determine the horizontal asymptote, we have to compare the degrees in the numerator compared to the degree in the denominator. Over here, you guys can see that the degree in my numerator is 1. So I know that 1 is less than 2. In your notes, there's something in that says where the degree in the numerator, n, was less than the degree in the denominator. That produces a horizontal asymptote of y equals 0. Not 0, but make sure it's y equals 0, because what that needs to tell you, if x equals produces a vertical line, y equals is going to produce a horizontal line. Does everybody follow me so far on my graph? Next thing is determining the x and the y intercepts. I showed you guys that little example over there. The x-intercept is when y is equal to 0. Well, obviously, ladies and gentlemen, we're talking about a function here, so we don't have an f, we don't have a y, we have an f of x. But the same process applies. You're going to replace f of x with 0 and then solve for x. 0 equals x minus 1 all over x squared minus x minus 6. Well, whenever you have a variable in the denominator, we got to get the variable off the denominator. So I can do that by multiplying by its reciprocal. I'm not going to multiply by the total reciprocal, like totally flip that over, because then I'd still have an x minus 1 in this denominator. It's not going to help me out over there. So I'm just going to multiply by this to get this off the denominator. And then I multiply it over here. And what happens? That divides to 1. This goes to 0. So I'm left with 0 equals x minus 1. So therefore, my x-intercept is x equals positive 1. Make a nice big point. OK? Oh, I'm sorry. I skipped number 3, slant asymptotes. We don't have slant asymptotes in this case. Now, step number 5.
Wait. On step 4, why do you multiply by, that's not the reciprocal because it's just over 1.
Well, I just want to get rid of what's in my denominator. So I'm multiplying by the reciprocal of that. That eliminates what's in that denominator. Right? If you multiply by the reciprocal, then you're still going to have, then you have an x minus 1 in the denominator. You don't want to have any variables in the denominator. So I'm just multiplying by what's in the denominator. OK? So now, the step next one is to find the y-intercept. Y-intercept, x equals 0. So in this case, I have f of x equals 0 minus 1 divided by 0 squared minus 0 minus 6, which equals 1 over 6. So therefore, if this is 1, 1/6 is going to look something like that. OK?
I have a question. Why are there y and x intercepts when the lines don't even touch them?
What?
Why are there x and y intercepts when this function doesn't even touch them?
It does. It touches them at 1/6 and at 1. It does touch them.
How? But it's not getting within it's getting within the dot dashed line.
Yes, you're correct. The vertical asymptotes are never going to be a part of them because these are rational functions. However, a horizontal asymptote, you can actually cross. You can have a value at a horizontal asymptote because a horizontal asymptote is not going to be restricting your domain. However, for a function, the vertical asymptotes restrict your domain. So therefore, we'll never cross a vertical asymptote. But it is possible to cross that horizontal asymptote. I just want you to remember that the horizontal asymptotes, the main important thing to understand about asymptotes is that's going to be what your graph approaches. It's possible for it to cross this asymptote, but it's going to approach the asymptote. And I'll explain that once we get to graphing. OK? Yes?
Wait, so is the y, why is x equal to 1 if you're changing the x to 0 and
I didn't. I replaced 0 with y, or in reality, f of x.
Yeah, I know, so then that would find the x intercept?
Yep.
You replace the zeros with y to
Yeah, because look at x-intercept, what is equal to 0? The y-coordinate, right? At y-intercept, what's equal to 0? The x-coordinate, right? So when I said, hey, I want to find the y-intercept, x equals 0. So I plug 0 in for x. Make sense? OK, yes? So
Is it 1 over 6 or is it negative?
it's negative 1 over negative 6, which reduces to 1 over 6. Yeah, just wait. The next thing is for us to text symmetry, which we're going to do f of negative x. F of negative x equals negative x minus 1 all over negative x squared minus negative x minus 6. Now, when you go ahead and simplify this, if you get the exact same answer, you have symmetry about the y-axis, right? If you get the exact same answer but with opposite signs, you have symmetry about the origin. Well, I'm not going to spend time simplifying this because I already know that my numerator is not the exact same as my numerator over here, and it's not the exact opposite either. Negative, positive. Those are opposites, but then that's negative, negative, which doesn't work. Does that make sense? Yes? So there's no symmetry. So you can just write no symmetry. OK? Now, the last thing we need to do is plot points. Yes?
So for the symmetry, you make all your x's negative?
Yeah, you're basically evaluating for f of negative x. And now in reality, you got to simplify this, which since you're having a question, I'll simplify it. You will. There's examples. I don't know if we'll do one today. But so here, when I plug in negative x and simplify, do I have the exact same function? No. Do I have the exact same function, but with everything being the opposite sign? No. So there's no symmetry. It's not even. This is nor an even nor an odd function. OK? However, there will be examples when you have even or odd. And what's nice about them, especially if you have even, you can just graph on the left side and then flip it over, right? And that's what's nice about even functions. Now, the table. All right? Basically, ladies and gentlemen, the table of values, you're going to want to pick some points. For those of you that don't have a calculator, you need to know what this graph looks like, right? So you need to evaluate this function for some other points. I would maybe evaluate for negative 1. I would maybe evaluate for 1, 2, 3. Plug in f of 3. Plug in f of 1, 2, 3, 4. Plug in 1, 2, 3, 4, 5. Oh, that's negative 4 and negative 3. And you plug those numbers in for x, and then find what f of x is, right? And then you'd plot them. If you have a calculator, or at least access to a calculator, you can type in your calculator and just go to the table function. And then that will actually tell you what they are without having to do all that algebra. And so for the sake of time, f of 5 is 0.28. F of 4 is 0.5. F of negative 1 is 0.5. That's negative 2.66. And f of negative 0.66. So this is just a little bit of example. But remember, this was like 1/6, right? So I was really like there. At negative 1, I'm at 0.5. So what this graph is doing is creating something like this. OK? Over here at negative 4, that's at 0.5. But then at negative 5, it's at, or at negative, I'm sorry, at negative 4, it's at 0.35. And here is at 0.66. What that graph is doing that. And then at 4 and 5, at 4, 1, 2, 3, 4, I'm at 0.5. And then at 0.25.
That's wrong. That's totally wrong.
Oh, no, I'm sorry. That's positive, not negative. Thank you. You're right. Those are positive. Positive and positive. OK, I'll show you exactly what I think. But yeah, those are positive values. Those are the negative, right? So that's what technically your graph would be able to look at. All I'm asking you guys to do is basically being able to, obviously you're going to want to plug in some points enough that you know what the graph shape is going to look like. But having a graphing calculator would be very, very helpful for you. Okay? The only difference is now we're going to be putting this stuff into motion. So I'm going to go over one, and then I'm going to give you guys basically one to go ahead and try on your own. And that's really basically all the time we have, although we will have more time on, as I mentioned on Friday, to kind of cover stuff. So you guys have h of x equals 3 divided by x cubed minus 4x. You guys can see I kind of have some steps here. The first thing is to identify your vertical asymptotes. All we simply need to do to identify vertical asymptotes is set our denominator equal to 0 and solve. So I basically go ahead and say my denominator here is x cubed minus 4x equals 0. Then I just go ahead and solve. Well, in this case, I can factor out an x. Does everybody agree with me that x equals plus or minus 2? Do I really need to spend time solving anymore? All right. So your asymptotes, if you guys remember, are going to be your dotted lines. Remember we talked about those in discontinuity? Those are going to be your lines that your graph is not going to be continuous on, right? So we have, so the first thing when you're graphing, I always like to first do my asymptotes. I'll go through that when we get to it. Not your butt. So the next thing is when we go ahead and take a look at this, step number 2 is to identify your horizontal asymptotes. So what the horizontal asymptote said, which was exactly in the same thing we wrote up there before, and which we've talked about and reviewed again, horizontal asymptotes is going to be, you're going to look at the degree of the numerator and the denominator. So the degree in the numerator, hopefully you guys understand, is 0. Okay? So n represents the degree in the numerator. D represents the degree in the denominator. In this case, when the degree in the numerator is less than the degree in the denominator, y equals 0 is your horizontal asymptote. Does everybody see that? OK. So now I create a horizontal asymptote at y equals 0. OK? Now, in the next case, now we simply need to, or sorry, y equals 0 is your horizontal asymptote. The next step, which is to check for symmetry, which is the exact same thing as what we did before where we're even and odd. But what's nice about checking for symmetry, ladies and gentlemen, is if you know you have symmetry, all you need to do is graph one side, right? And then you can just reflect it based on the symmetry. So to check for symmetry, all we're simply going to do is evaluate for f of negative x. So therefore, that's 3 over negative x cubed minus 4 times negative x. So as you guys can see, do I have symmetry here? Is this the exact same? No. So therefore, it's not symmetrical about the y-axis, meaning this is not even. However, do I have the exact same but opposite signs? Basically, could I factor out negative? Yes, I do. So guess what? This is symmetrical about the origin, meaning whatever I have here, I can just, well, not on the other side. That would be symmetrical about the y-axis. Here, I can just reflect and then reflect over. You reflect over the x-axis, reflect over the y-axis, like reflecting over the origin. Okay? And I'll show you exactly my example. Now, step number 4 is to choose points. All right, here's where it kind of comes into a discrepancy. And I'm kind of going low on time, so I'm gonna do it the shorter way. But I will show you guys at least a couple ways to identify this. What I recommend you guys doing, if you do not have a graphing calculator, is to choose 2 points. Did I not right there? OK. My recommendation is to choose 2 points to the left and to the right of each asymptote so you understand what the graph looks like. If you have a graphing calculator, you can just graph it and then click the table value and figure out what it is. If you're doing your homework, I would plug it into Google so you can still see what the graph is. But you're going to want to make sure you guys can evaluate for points. So what I'm going to do is let's evaluate. I'll just evaluate for these 2 points to the right. OK? So I'm going to evaluate for f of 1, 2, 3. So let's evaluate for f of 3. What happened to 1x?
For step 3, when it's -4 times -x,
Yeah.
Huh?
step
Where did it go?
3, right there. Yeah, that x right there, where did it go?
Oh, it's there. Sorry. So that becomes 27 minus 12 is 15. Right? 3 over 15 is going to be approximately 1/5, which we can rewrite as 0.2. Only time when I'm graphing do I like writing them as decimals. OK? Then let's go ahead and check into, let's do f of 4, see what that gives me. So if I did f of 4, I'd get 3 over 4 cubed minus 4 times 4. So 3 cubed is 64, right? Minus 16 is going to be 48. So 1/16, which my calculator shows me, is 0.0625. Do you guys see the pattern? Where is this going closer and closer to?
Origin.
Well, no, what number is this getting closer and closer to? 0, right? So what I want you guys to understand, listen. Through these 2 points, what are the asymptotes? Asymptotes, we know the graph cannot cross at the vertical asymptote, right? Asymptotes, vertical asymptotes represent values that make the graph discontinuous, correct? That means they're not a part of the graph. That means they're not a part of the domain. So we use these asymptotes, all right, to help us with our domain. But it's also, what's important about the asymptotes is that's where the graph approaches. Your graph approaches your asymptotes. So if my point's here, the next one's closer to 0, do you guys agree with me that it's going to keep on getting closer and closer to 0? Right?
Yeah.
But then it also has to go down and approach this asymptote. So it's going to look something like this. OK? Yes? Did I write in the? Oh, those are positive, aren't they? Oops. I wrote those as negative for some reason. Thank you. Sorry about that. Exact same thing. For some reason, I wrote these as negative. I don't know why. OK. So
that's the last one.
that's those. And then you would have to pick points in between here to figure out what these values are and what kind of shape this goes through. Well, since it has to approach these 2 asymptotes, you could plug in 2, but really in your calculator is going to be the best. And what you guys will see is this is going to approach like this. Now, listen. How can I use symmetry? Remember, I said this is symmetrical, right? It's symmetrical about the origin. So therefore, you reflect it over the y-axis, reflect it over the x-axis. So therefore, the graph, the sketch of the graph, is going to look like this. And that's my final graph. Done.
All right. So let's go and talk about asymptotes, right? First thing that the problem is asking us is they want us to find our domain and also find our vertical and our horizontal asymptote. So first thing, guys, if you remember when we're talking about domain for a rational function, what we need to do is we need to say your domain is going to be all your values except for anything that's going to make your bottom 0, right? Because we cannot divide by 0. So therefore, let's go and figure out what values will give us 0 on the bottom. So when I want to find out when I want to find the domain, I'm going to find the zeros of my denominator. So I say 0 is equal to 1 plus 2x. Right? So therefore, I take a look and I solve for x, subtract 1 on both sides. So therefore, when I plug in the number -1/2 into x, I get 0 on the bottom, right? Right?
Yes.
So when I plug in -1/2 into the bottom, I get 0. Meaning, we cannot do that. So if I was going to look at my graph, I'll just make the graph one up. If I had a graph, and like I said, I have no idea what my graph's going to look like. However, I do know that at -1/2, my graph is not, you can't have -1/2, right? That cannot be a part of my function. You cannot put in -1/2
and get an output because you can't divide by 0. So therefore, what we have is what we call an asymptote. And if I look, let's say -1, -2. So therefore, at this point, -1/2, I'm going to draw this vertical line here. I have no idea what my graph's going to look like, but I know at -1/2 that is not a part of my domain. So my domain is going to be my all real numbers, except x cannot equal -1/2. So to graphically represent that, what we do is we have what we call a vertical asymptote. So you have this dotted line. Now the next one is now I need to figure out what my horizontal asymptote is. So your vertical asymptote is you pretty much find the zeros of your bottom polynomial. To find the horizontal asymptote, I need to take a look at the 2 degrees of my leading terms, or each polynomial. What I'm going to do is I'm going to rewrite this polynomial as leading coefficient, or my leading terms in front of each other. So here what I have is, remember we always have your highest degree, x's then you're going down. Well, these only have x to the first power on each one. So you can say x equal to 1 and x is equal to 1. And we call them a lot of times m and n, right? We just give them kind of our variable names. What they're saying is when your top degree is equal to your bottom degree, what you're going to do is you're going to take your coefficients and divide them. So since I have 1 is equal to 1, my degrees are exactly the same. All I'm going to do is I'm going to take my top degree, which is -5, and divide it by 2. So I'm going to take -5 divided by 2, and that's going to give me a -2.5, right? So therefore, my horizontal asymptote is going to be down at -2.5, and that's going to be a line right there. So, the graph didn't ask us to graph these all, but I just want to kind of give you guys an idea of, physically what it's going to look like, what these asymptotes actually look like. And what you can see is the graph is these asymptotes are never going to cross or approach these lines. So to find the vertical asymptote for this problem, what you have to do is just set your bottom polynomial equal to 0, find the value of x, that's your vertical asymptote. And to find the horizontal, there's a couple range of powers we'll actually talk about. But the first one is when you have your degrees for each polynomial are exactly the same, then you just take the coefficients, divide them, and that's going to be your horizontal asymptote. Once I found my vertical asymptotes first, when going for my graph, I'm going to go over to +2 and to -2, and I'm going to create dashed lines. Now remember your asymptotes. Vertical asymptote, your graph is never going to intersect. But the important thing about an asymptote is that is going to be the line that your graph is going to approach. So we know our graph is going to approach these lines. Okay? So when you're thinking about that, even if you don't know what the graph looks like, you know that the graph is going to approach them. Next thing, find our horizontal asymptotes. Horizontal asymptotes, basically we're looking at the degrees of each of them. So degree in our numerator over the degree in our denominator. And what I state is when the degree in the numerator is equal to the degree in the denominator, y equals a over b, where a and b are the leading coefficients. So my degrees are exactly the same, right? So the leading coefficient of my numerator is -3. The leading coefficient of my denominator is 1. So my horizontal asymptotes, I could say d is equal to n. The degree in my denominator, in my numerator, is equal to my denominator. Therefore, y equals -3 over 1, which is just the same thing as y equals -3. Does everybody follow me? Anybody have any questions? Whatever else. Then the next thing is I don't need to do 2a because that's for slant asymptotes. For number 3, I need to check for symmetry. Check for symmetry, if you guys remember, when you plug in f of, sorry, I wrote that in wrong. When you plug in f of -x, when you plug in f of -x and you get back f of x, that tells you what type of function you have. Even. If you plug in f of -x and you get back negative f of x, that tells you have odd. So what I'm going to do is I'm just going to plug in f of -x. Okay, what I get out is 3x squared minus x plus 12 over x squared minus 4. Is that the exact same as my original? No. Is it the exact opposite, mean everyone has the opposite sign? No. So guess what? There's no symmetry. No symmetry at all. Why is symmetry nice? Because symmetry is nice because if I know there's symmetry across the y-axis, I can just choose points to the right and then just reflect it over. Does that make sense? So having symmetry is nice, all right? And you guys should be fairly quick with how to be able to check symmetry. Next thing, so we don't have any symmetry. So guess what? Now what we're going to have to do is just choose points. All right? And this, again, is where kind of like your calculator comes in handy. Basically, ladies and gentlemen, we know that the points that make up our basically what we're going to do is plug in points for x and find their values. So I always like to do 2 points to the left and to the right of each asymptote. So in this case, I would do -1, 2, 3, 4. So I would evaluate for f of -4, f of -3. I'll do f of -1. The middle is always kind of difficult, so I'll do f of 0, f of 1, f of 3, and f of 4. Okay, you're still going to want to show me what these points are. Even if you have a calculator, I'm going to still need to see at least what exactly is 1 point to the right or to the left. Yes?
Wait, you said that it was good. It was like helpful sometimes if there's no symmetry.
No, if there is symmetry. Because look, if there's only symmetry, all I need to do is find points to the left, and then I could just reflect it over, right? But there's no symmetry, so I don't know what this graph looks like. So if you don't have a calculator, do 2 points to the right and 2 points to the left of every asymptote. If you have a calculator, you can use your calculator to aid you, but you're still going to need to show me at least a point to the left and to the right. So basically, you're just going to do -3 times -4 squared plus -4 plus 12 divided by -4 squared minus 4. So that becomes 16. That becomes -48. Let's see, that's going to be -48, -52, -40. Divided by 16 minus 4 is going to be, 16 minus 4 is going to be 12. So therefore, that approximates to, just give me the decimal. Anybody have the decimal form of that? Assuming my math is correct. Anybody? OK. I will follow. I will pick up the slack. Sorry, what is it? Oh, shoot. I forgot to write in the asymptote. We also have this horizontal asymptote, right? So we got to plot that. My apologies. So I do -40 divided by 12. To speed this along is -3.33. So at -4, I'm at -3.33. OK, let's do -3. If I plug in -3, that's going to be 9. So that's going to be -27, -30, -30. So that's going to be -18 over 9 over 5. Does everybody follow me? I'm doing my math in my head. -18 divided by 5 is a -3.6. OK, so let's look at this again. If you guys can see, this graph has to go through these 2 points, right? Has to go through these 2 points, which is a -3.66. And has to go through these 2 points, and it also has to approach this asymptote and that asymptote. The only way for us to do that is to kind of have a curve like that. Does everybody agree with me? Yes? No? Maybe so? All right, let's do -1. If I plug in -1, -1 squared is 1. 1 times -3 is -3. Plus -1 is going to be -3, -4, -4. So that's going to be 8 over -3. So at -1, I'm at negative 2.66. So at negative 1, I'm at negative 2.66. Let's check in what 0 is. 0, 0, that's going to be 12 over negative 4. So at 0, I'm here. I'm actually on the asymptote, which is OK for a horizontal asymptote. Let's check at number 1. If we plug in 1, so you plug in 1, you'll have negative 3, negative 2. So negative 2, that's going to be 10 over 1 squared is 1 minus 3 is negative 3. So 10 divided by negative 3 is negative 3.33. So at 1, I'm at negative 3.33. All right. So how do I graph something that goes through these 3 points, okay, but converges to this asymptote and converges to that asymptote? Well, when you guys get enough practice with this, you'll see it's going to look something like that. OK? And then if I just go ahead and apply 3 and 4, since I have this graph in my graphing calculator, I'm just going to go to my table function to save me time. And on my table function for 3, it's negative 2.4. And for 4, it's negative 2.67. So now you just connect these points. OK? Yes, Elise, questions? No? OK. So ladies and gentlemen, for this one, what we need to do is we need to find the vertical, horizontal, and we're going to see if there's horizontal, and we'll prove. Then if there's slant, then we're going to check for. So first, let's do the intercepts. And then what we'll do is we'll go back and we'll check our solution points. Or not our solution points, I'm sorry, our intercepts. And then we'll check our solution points. So the first thing I think is always easiest to start off with is the vertical asymptote, because our vertical asymptote is when our denominator is going to equal 0, correct? So first step, vertical asymptote. It's the easiest one to do. Vertical asymptote is equal to when x minus 1 equals 0. So just take your denominator, set it equal to 0. Vertical asymptote. Solve here. This one's pretty easy. You could probably do this in your head. You notice that x equals 1. Okay, so I'm going to erase this. So I'm just going to put your vertical asymptote right now is x equals 1. All right. Now the question here doesn't ask us to find the horizontal asymptote, and let's ask why. Because let's pretend they just say find the asymptote. So the next thing you'd want to do is look for the horizontal asymptote. So what we need to do, remember, is we need to compare the degrees of our polynomials. We have a polynomial in our numerator and a polynomial in our denominator, right? So we look at them and we say, are they in descending order first? Yes, we put them in descending order. Then which is since my numerator degree is greater than my denominator degree, right? So whenever you have the numerator, by your test that was in your notes that we wrote down, whenever the degree in your numerator is larger than the degree in your denominator, we have no horizontal asymptote. OK? So I'll write this to the side because I'm going to delete it. All right? So when you have no horizontal asymptote, what you have then is a slant or an oblique. All right? So here's how you solve this. All right? And here's going to be your one example. I already have multiple examples. Hopefully you guys already saw those that you work with. So how do you find your slant asymptote? Vertical, you set it equal to 0, right? Horizontal, you do the test, and that determines what it's going to be. For slant asymptotes, since this has a smaller degree and this one has a large degree, that means I can divide x minus 1 into this, right? No. You can't. This is divided by all those terms, so you just can't cancel it out of one term. So what I'm going to do is I'm now going to use long division. So I say x minus 1 divides into x squared minus x plus 1. So for those of you that were like, oh, I remember long division, I got it. But for those of you like, ew, I never liked long division, I just did synthetic. Well, now we got to keep on going practicing with that long division. So x goes into x squared, x times, correct? Then I do x times x, which is x squared. X times negative 1 is negative x. Then remember, we put parentheses and subtract. X squared minus x squared is 0x squared, which is 0. Negative x squared minus a negative x squared, which is going to be, again, 0. Bring down the 1. Does x divide into 1? No. So we write plus 1 divided by your remainder, right? Now, I'm not going to try to get too much into calculus with you guys, but what you guys will notice as these numbers keep on getting larger, as x keeps on getting larger, the number in general gets smaller, okay? So eventually, as x keeps on getting larger, this number eventually goes to 0, all right? Kind of end of story. If it's not really making sense, you'll learn more about it in calculus. However, our slant asymptote is just going to be our quotient without the remainder, because the remainder ends up going to 0. So our slant asymptote is going to be the line y equals x. All right, so you just take whatever the quotient is without dealing with the remainder. So my slant is equal to y equals x. Okay? Does anybody have any questions on that? Yes?
So does that reflect the state?
Yeah, I mean, that just means you don't have a horizontal line. Now you have a slant. So yeah. Yes. No, now we have to go back and do those intercepts again and the solution points. So I'm going to do that again for another problem. Yes?
Don't get y equals x.
So remember, so this divides into it by x, right?
Yeah.
So that's going to be your solution or your quotient of your problem. As we look at it, when we look at the graph, it might make a little more sense. But you're just going to take this. We know it divides into that. Well, it divides into their x number of times. So that's just going to be your creating. That's just going to be the slant asymptote, what your graph is going to approach. So when we look at a graph, it might maybe make a little more sense as why this value is going to work. But just remember, do not include your intercept or do not include your remainder. It's just going to be your quotient, whatever the quotient line is. All right, so we good with, yes?
Do we only find slant when it's like
Only going to be slant when you have no horizontal. Yep, there's not going to be a slant if there's a horizontal. Okay? We good? Yes?
So if there was no remainder, would you put y equals whatever it is?
Yeah, it's still, even if there's a remainder or if there's no remainder. Well, when we have no remainder, it'll be a different scenario, okay, which we'll talk about later. But you should always have a remainder, but that remainder we're just not going to deal with, okay? Okay, so we're all good with that. Now, the next point is finding our x and y intercepts, right? So you guys have to do this for your previous homework as well. So let's write it out. X-intercept is when f of x equals 0. Y-intercept is when x equals 0, right? Write that down, guys, and say, all right, for every single one of my problems where it says find the x-intercepts and y-intercepts, I need to do these two cases. All right, you guys should be, once you start getting good at this, you don't need to keep on writing that down. So f of x equals 0. So you just put 0 in for f of x. Here, you put 0 in for the x's. Okay, you guys see the difference? One, you put 0 for f of x. The other one, you put 0 in for the x's. Right? Okay. So now, let's do this one first, because this one's the more difficult. So how do you solve for this? Well, to find x, you got to get the denominator at the bottom. So you multiply by x plus 1. So you have 0 equals x squared minus x plus 1. Right? So ladies and gentlemen, when you have a trinomial in this format and you need to find the values of x, what technique are you going to want to use? Unfoil, which would be like the factoring technique, right? You've got to factor this. So we look at this and say, what two numbers multiply to give you positive 1, but add to give you negative 1? Is this factorable? No, it's not factorable, right? So we need to see then, if it's not factorable, let's just, yes?
Whenever you multiply the denominator to get rid of that or whatever, do you always do the opposite like you did? Because on 25.
No, I don't know what I'm doing. I don't know why I did multiply by 1. Thank you. No, you just multiply by what the denominator is. Because then those are going to cancel out, right? If you multiply by plus 1, those wouldn't cancel out. Yeah, sorry. I don't know. I was just trying to do this too quick, I guess. So we just need to look. This is not factorable. So let me go and see. Let's go and see if then. So it's not factorable under real numbers. Let's see it's factorable under irrational numbers. So how can I still find the values of this? Quadratic formula, right? So you could do opposite of b, which is 1, plus or minus negative 1 squared minus 4 times a times c, which is 1, divided by 2 times 1. Now what I look in here is I notice automatically this is our discriminant. And you could check your discriminant. You notice that negative 1 squared is 1, right? Minus 4. You're automatically going to have 1 plus or minus the square root of negative 3 divided by 2. Now, whenever we take a negative square root of a negative number, we're going to be dealing with what? I, which is imaginary, right? Therefore, we can't write an imaginary intercept. So therefore, does this have a real number intercept? No. So does it cross the x-axis? No. So you can say no x-intercept.
Could you use synthetic division?
No, because I mean you're not dividing into there. So to find the remainder though, you could have done synthetic division, or to find the slant asymptote. Since this was a binomial to the degree 1, you could have done synthetic division.
So the only way you can find whatever is the quadratic.
Well, no, I'd want you to factor it. I mean, if this was factorable, then you could factor it.
Well, yeah.
But it's not factorable, so you have to do that.
So it's factorable, then you would get down to 2.
Yeah.
You'd have 2 x-intercepts.
Yep. Mm-hmm. Or you could have 1 where it's like, it could be like 1 x plus 1 squared, right? And you could have 1 with the something like that.
So you couldn't just solve for x, you know what I mean?
I mean, no, because there's 2 of them, and 1 has a power of 2. So you can't just solve for x. You got it. You have, whenever you have a trinomial, you have to use factoring technique. Yes?
So every time it's not factorable, there's no x-intercept?
No, this could be, not necessarily. This could be a positive square root of 3. That just means you'd have an it just means your number is not a integer. So you could have like an irrational number as your intercept, or as your intercept where it crosses. Okay, so this is just one case where you don't have a real number as your intercept. But it could be, this could be non-factorable, but it could still be positive. Okay, so opposite 8 times c, yeah. But it is possible for, even for not to be factorable, but for it to still be a real number, just not an integer. Okay? So now we find this one, which is pretty easy. Hopefully you guys get this one. This one's going to be equals negative 1. All right? So my graph, if I was going to graph it, which I'm not going to ask you guys to do, but my graph right now, what do we know? We know x equals 1 is a vertical asymptote, right? And our slant asymptote is y equals x, which looks like that. That's y equals x. This is x equals 1. So that's your vertical, that's your slant. And the only thing we know is it has a y-intercept at negative 1. Right? It doesn't cross the x-axis, right? Now we got to choose 2 points to the right of your intercept or your vertical asymptote and 2 points to the left. All right, now 0 is already taken, so you can't use that. Sure, let's just do negative 1 and negative 2. Negative 1, negative 2, and let's do 2 and 3. That's fine with me. Okay, so just pick points to the left and to the right of your asymptote. Now, ladies and gentlemen, does anybody have this table that they can tell me what they are? Because we don't have time to go through them. So you guys can plug each one of those values in and figure them out. Or what you have is negative 1 is negative 1.5, negative 2 is 3, 2 is 3, I'm sorry, negative 2 is negative 2.33, and 3 is 3.5. Okay, so if we look at my random graph that I'm making, -1, I go down now to -1.5. At 2, so it's going to look something like that. At 2, 1, 2, I'm going up to 3. And then at 3, I go to 3.5. Looks like that, all right? I believe I remember the shape of the graph is going to look something like this. All right? Again, you guys don't need to know. I just need you to prove to me what you know your solution points, okay?
They all not, are some of them going to be able to factor though, like on the x-intercept, it won't be as complicated?
Yeah. But you see how there is no x-intercepts on this graph? Right? Do you see how it doesn't cross the x-axis? Right? So that means when you find that there has to be imaginary x-intercepts. But obviously, if it crosses the x-axis, then it's going to be a factorable problem, right? You still should know the quadratic formula, or if anything, you should at least know how to determine the discriminant. All you really need to do for this, well, yeah, you should know the quadratic formula, but once you know that your discriminant is negative, then you already know you have imaginary roots, okay? Or imaginary x-intercepts. So on this one, ladies and gentlemen, they're asking us to graph it, all right? So automatically, we're just going to go through the steps. The first thing to graphing it is we need to determine the vertical asymptote, all right? Remember, the vertical asymptote is when our polynomial in our denominator is equal to 1. So I write x plus 2 squared, I'm sorry, not equal to 1, but equal to 0. So we know that the values that our polynomial will take on when they're equal to 0 are going to create our vertical asymptote. So now I simply need to use solve for x. I can use the square root method, which means I'm going to take the square root of both sides and get x plus 2 equals 0, subtract 2, x equals -2. So now I'll plot an x and y axis. So I go over to -2, and I create my nice little vertical asymptote. Right? OK. Now let's go and take a look at the horizontal. When looking at the horizontal, remember we need to look at the degrees. Now, ladies and gentlemen, these are not multiplied out, correct? These are not FOILed out. However, if you notice, this is going to be x plus 1 times x plus 1 times x plus 1. This is going to be x plus 2 times x plus 2. When I multiply that out, the highest degree that this polynomial is going to be 3, and this one will be 2. So therefore, on my horizontal, we have my numerator is larger than my denominator, right? Whenever your numerator is larger than your denominator, how many horizontal asymptotes do you have? 0, right? So you do not have a horizontal asymptote. So we can say A is greater than B, which is your degree. So therefore, we have no horizontal asymptote. OK? So this will be important on your homework to make sure you guys are writing those down. So we have a vertical asymptote at x equals -2, and we have no horizontal. All right, now the next two important points is let's find the x and y intercepts. So we want to find the x-intercept, and we want to find the y-intercept. Remember, the x-intercept is where the graph crosses the x-axis. So when the graph crosses the x-axis, we know y equals 0. For the y-intercept, that's where the graph crosses the y-intercept, or the y-axis, so we know that x equals 0. So now to plug y equals 0, well, I know I don't have a y, I have an f of x. But y and f of x are both the output values, so we're just going to say 0 equals x plus 1 cubed over x plus 2 squared. So again, ladies and gentlemen, how do you solve for x? You have an x in the numerator, denominator. Well, first of all, we need to get the x plus 2 off the bottom, right? So I multiply by x plus 2 squared on both sides. Those now divide into 1. This multiplies to 0. So I'm left with 0 equals x plus 1 cubed. So now, how do you solve for 1? Well, let's get rid of the cube, right? So I cube root both sides. And I'm left with 0 equals x plus 1. Subtract 1, subtract 1. My x-intercept is when x equals -1. So I go over at -1, and I say that's my x-intercept at x equals -1, right? Because it's -1 comma 0 is the point. So now to find the y-intercept, what I'm simply going to do is now, to find the y-intercept, I just plug 0 in for x. So I say f of x equals 0 plus 1 cubed over 0 plus 2 squared. Well, 0 plus 1 is 1. 1 cubed is 1. 0 plus 2 is 2. 2 squared is 4. So therefore, my y-intercept is at 1/4, which would be somewhere right there. All right? Now, ladies and gentlemen, all I asked you to do was to find 2 points to the left and then 2 points to the right of your graph, correct? That's all I asked you guys to do. Now, I've already found 2 points to the right, so that's good. So let's just find 2 points to the left. So we know we can't evaluate for -2, so let's do -3 and let's do -4. So I'll do f of -3 equals -3 plus 1 cubed divided by -3 plus 2 squared. -3 plus 1 is -2. -2 cubed is going to be -8. -3 plus 2 is -1. -1 squared is 1. So therefore, my answer is -8. So at -3, 1, 2, 3, I go down -8. 1, 2, 3, 4, 5, 6, 7, 8. Now let's do f of -4. So -4 plus 1 is -3. -3 cubed is equal to a -27. -4 plus 2 is going to be -2. -2 squared equals 4. So 4 goes into 27, let's say 6, right? So -6 3/4, or -6.75. So at -4, 1, 2, 3, 4, we're down only -6 and 7.75. So 1, 2, 3, 4, 5, 6. So we look something like that. Well, that's not right. Oh, yes, I'm sorry. OK, that is right. So what you'll notice, ladies and gentlemen, as we go ahead and graph this, all right, what we'll notice is these 2 points, they actually come around. And what we know is this graph has to approach these asymptotes. So when you guys look at your graphing calculator, you're going to want to make sure you provide these points and your vertical and horizontal asymptote. And then what we'll be able to determine now is that the graph is going to approach these asymptotes. So I think it looks something like this. And then here, I don't even know what my notes again look like. Yeah, so it looks something like this. So just by picking 2 points and using a graphing calculator, you guys can at least verify the 2 points that the graph goes through. But then the main important thing, guys, for you to understand is that the graph approaches these asymptotes. If the graph goes through these 2 points, it's a little bit difficult unless I was using my graphing calculator to really see exactly the shape of the graph. But all I'm really asking you guys to do, it's OK if you're not exact on your graph, because I know some of you have graphic calculators, some of you do not. As long as you can show me your vertical, horizontal, x and y intercepts, and then 2 points to the right and 2 points to the left, we're good to go for this, OK? So I'm not going to make sure, we're not going to be trying to be exact on graphing. You guys have technology for that, all right? All I want you to do. There's no difference, ladies and gentlemen, in me saying x plus 3 divided by x minus 3 divided by x squared minus 9 over 3x minus 9. This is the exact same thing. See, doesn't matter which way you write it. Last class period, we wrote it like this. Here, I'm just writing it as a fraction divided by a fraction with a fraction bar instead of a division symbol. So it's the exact same type of problem. All right? So again, just like we did before, we want to simplify. Now, according to, actually, I'll write it down below. So we have x plus 3 divided by x minus 3. I can't simplify that. However, x squared minus 9, I can simplify to x minus 3 times x plus 3. And 3x minus 9, I can simplify to 3 times x minus 3. Now, what did we do over here when we had a fraction divided by another fraction? We recreated it as multiplication by multiplying by the reciprocal, right? So what we're going to do is multiply the top and the bottom by the reciprocal. Well, if you guys remember, the reason why we did that, multiplying by the reciprocal, is because the division property applies for every term in the denominator, right? Anytime you take a denominator or a number or expression and multiply it by its reciprocal, everything goes to 1. Right? But we have to do the same thing up on the numerator. So when we do it in the numerator, we could see x plus 3 divides by x plus 3, x minus 3, and x minus 3. And therefore, Anna, the only thing we're left over is 3 over x minus 3. So the main important thing is that it's a complex fraction. The first thing you're going to want to do for every single example you guys do is simplify. Look at every numerator and denominator of each fraction and simplify it. Well, 4x I cannot simplify any further. Nor can I simplify x plus 6. However, x squared minus 3x, I do notice that those have an x in common. So I'm going to factor out an x. Does everybody follow me with that? Factor out an x. And then in my bottom, in my denominator of my denominator, I'm going to factor this in my head because I told you we're going to start moving quicker. Yes?
Isn't it 3x?
We're like here? I factor out the x, so you can always check your work. If you apply distributive property, x times x gives you x squared. X times negative 3 would give you negative 3x. Got it? So now in this one, though, I'm going to factor using the tree, which we already did that other distributive property. I'm not going to spend time going through that method again. If you need help with that, come and see me. This could be factored into x plus 6, x minus 3. Basically, what I did was I said, what two numbers multiply to give me negative 18, and then add to give me a positive 3. That's how I came up with that. Now, basically, what I try to reiterate for everybody is whenever you're trying to get a fraction off the denominator, the best thing to do is multiply by its reciprocal. So I'm going to multiply by x minus 3 times x plus 6. X times x minus 3. The reason why multiplying by its reciprocal works is that division property. You guys notice that the division property you can see that the x minus 3 and the x minus 3 divides to 1. X minus 3 and x minus 3 divides to 1. X plus 6 and x plus 6 divides to 1. And the x divides times 1. So anytime you have a rational function or a fraction in the denominator, yes, question? I multiplied the blue by its reciprocal. So I put the denominator in the numerator, and I put the numerator in the denominator. Anytime you have, the reciprocal of 1/4 is 4 over 1. All I did was flip them and multiply them. But what's nice is multiplying them, since every single expression, do you guys see how all of these are separated by multiplication? They're all separated by multiplication. Each expression is separated by multiplication. So that's why I could cross out or basically divide to 1, right? However, though, whatever you do in the denominator, ladies and gentlemen, you have to do in the numerator to produce equivalent fractions. You just can't take 4 over 5 and just multiply the bottom by 2. That's 4 over 10. That's not the same. But if you did 4 over 5 and multiplied by 2 over 2, then you'd have 8 over 10, which is the same thing as 4/5. Do you guys see that? So I have to multiply by my reciprocal, x minus 3 times x plus 6 over x times x minus 3. And what you guys can see when I now go ahead and do that, they both had an x minus 6. OK, you could have simplified that before, but whatever. Now you can see that by applying the division property, the x plus 6's divide to 1. The x minus 3's I could have divided earlier, but they are going to divide to 1. And the x over the x divides to 1. Leave me with a final answer of 4. Got them?
There are 2 names that aren't in here.
2 names that aren't in there?
Yeah, so I just put them.
All right. Now, one thing I want to go through, guys, is we could do this the way that the last method I told you, by adding these equations up and then dividing them, right? So it makes sense. You can add them up to the side, see what they get them to one rational expression, and then you can divide them. There's another thing. When you guys were learning equations, one thing we had is, let's say I had like 3/4 x plus 1/8 equals 11/12. Okay? If you had a problem like this, all right, one of the ways to solve an equation like this is what we call like fraction busting. Just get rid of all of the fractions, right? So what we would do is we'd multiply everything by our least common multiple, our least common denominator, to get rid of the fractions. So if you had an equation like this, right, guys, none of them have the common denominators. This would just be a mess trying to do all fraction operations, right? Yes? Would anybody want to do this? No. But what you could do, if I said, all right, the LCM of all my denominators equals 12. So if I multiply all of my denominators by, or every single term by 12, is my equation still equal? As long as I do whatever I do on the left side, I do on the right side, is that good? So since I multiplied both terms by 12 on the left side, I multiply on the right side, my equation is still true, right? OK, but now what happens? That goes to 1. OK? That goes to 3. And this would now, simplify down to 3/2. So I don't get totally rid of everything. However, is this a lot easier to go and work with than what the previous problem was? I didn't get rid of all the fractions, sorry. But I made it simplified, right? So that's the exact same thing. Notice, though, guys, as long as we do it to everything, we keep the equation equal. Well, that can be the same thing when you have a rational expression. As long as you multiply your numerator and your denominator by the same number, you keep what we call equivalent fractions. So what would be my number, or what would be my value that I'd want to multiply the numerator and the denominator by? Well, in an equation, when I had fractions, I multiplied by the LCM. So do you think I might want to multiply by the LCM for my fraction? Yeah. So let's go ahead and determine what is the LCM then of this expression. So here I have a denominator x minus y. Here I have a denominator x plus y. And here I have a denominator of x minus y. So what do you think the LCM would be for those two? What do you say, JD? There you go. So what I'm going to do then, ladies and gentlemen, is I am going to now multiply my numerator times x minus y, x plus y. And I'm going to multiply my denominator by x minus y times x plus y. Does everybody understand that these are going to be equivalent equations? Yes. Everybody agrees with that? No? Okay. Well, Dimitri.
I say no.
No, I'm just kidding. So if you had 3/4, right, and you multiplied by 2 over 2, you would get 6/8. Is 6/8 the same thing as 3/4? Yeah. Of course it is, right? Good job. OK. So now we have to apply. Here I have an expression. So I need to apply distributive property. Well, ladies and gentlemen, when I apply distributive property, the x minus y divides with the x minus y to give us 1. So therefore, I'm only going to be left with 2 times x plus y. When I multiply x minus y times x plus y times this, my x plus y and my x plus y divide to 1. So I'm just left with x minus y. When I multiply my common denominator, or my least common multiple, times this, my x minus y and my x minus y divide to 1. So I'm just left with x plus y. Any questions on that step? Yes, Ashley. You have that great look. OK. So now what I'm going to do is I can't break this up because I have this addition. So you can't just say, oh, those divide out, because you have addition separating them. So what I want to do is now simplify this to give me 2x plus 2y plus x minus y over x plus y. Then we'll move it this way. And we'll say 2x plus x is 3x. 2y minus y is going to be y all over x plus y. And no, ladies and gentlemen, those do not cancel out to leave you with a 3, because you'd have to factor out a 3 for them to be able to divide out. So that would be your final answer. OK? Alex, did you have that written down? Do you? OK. Ready. What I'm going over right now, guys, is really nothing new. There is a couple things we want to talk about. First of all, you may be asked about the restrictions on the domain. Remember, we talked about this day 1. So the first thing you want to look at is what values will make the denominator 0. And you can see there's a lot of different fractions, a lot of different things going on here, right? So just to let you guys know, you can see that here's a denominator, here's a denominator. I don't want to underline them. It would be too many fraction bars. But if you guys can see, there's 3 different denominators, right? So we want to find the values that are going to make those zeros, because those are undefined values. So we can say x cannot equal -3, -4. And then here, you notice that this is conveniently factored to x plus 3 and x plus 4. So I don't need to rewrite that, correct? However, I also have this as a denominator. Don't you guys agree? So therefore, I need to set that equal to 0 as well. Now again, what you guys will notice is this isn't that big of a deal. If you set this equal to 0, basically you're multiplying the denominator on both sides, so you really have the numerator equal to 0, correct? So when you solve the numerator equal to 0, does anybody see what we get here? Complex number? Yep, question? So when you go ahead and subtract and divide by 3, you get negative. Well, can you take the square root of a negative number? No, so it's going to be a complex number. So therefore, this is not a restriction on your domain. So we don't really need to worry about that. So the only restrictions on our domain right now are -3 and -4. Now what we need to do is simplify. So we can look at the restrictions, and now we're going to go ahead and simplify. So the way that I like to simplify is just like how I taught last class period. Identify the LCD and multiply everything by the LCD. So we identify the LCD is basically just going to be the product of 2 denominators, x plus 3 and x plus 4. Because obviously this divides into that, and these two both divide into that. So as I multiply everything times the LCD, when you multiply this, what divides out? X plus 3. So you're just left with the x plus 4. When you multiply this times that, what divides out? X plus 4. So you're just left with the x plus 3. And then when you multiply this times the denominator, you can see that both of them divide out, right? So you're just left with 3x squared plus 1. And now all we got to do is simplify it. And that's it. So if you multiply everything times the LCD, get rid of those extra denominators that you have, and now you just have something to simplify. So we can apply distributive property. So we have x plus 4 minus 2x minus 6 all over a 3x squared plus 1. And then we combine like terms, and we get a negative x minus 2 over 3x squared plus 1. Now, the only thing we want to do once we have simplified it is see if there's been added any other constraints. And as you guys can see, the only values that make this denominator 0 would be those imaginary numbers. So my final answer on my multiple choice test would be x cannot equal -3 and -4. And that'd be your simplified answer. OK? You guys can see I have a lot of fractions here, right? a lot of fractions. So just like in solving, yes, ladies and gentlemen, these do not have common denominators. So yes, you could find the common denominator and then add them, right? However, what I think is the easiest thing to do is identify the common denominator and then multiply, like we did for solving, multiply every single term by that common denominator to eliminate your denominators. So the first thing we want to do is factor to find our leading coefficient, our common denominator. Here, I can factor out a 3, so that would give me, what? I didn't hear you, I'm sorry. Yep, 3 times x plus 5. Here, I can factor out a 4, so that's going to give me 4 times x plus 5. OK? It was 4x plus 20. So now what I want you guys to understand is my common denominator is not just x plus 5, but it's also the common denominator of 3 and 4, which is 12 times x plus 5. Basically, I mean, for those that works. Huh? I'm not done yet. Now, as I mentioned, I'm going to multiply every single term like I did for the equations. It's the exact same thing as the equations. You're going to multiply everything by your LCD. 12 times x plus 5. Why? Because all of the terms, x plus 5 divides into all of these, and 4 and 3 and 1 all divide into 12. Now, and that's what you want. You want your denominators to all be able to divide into your LCD. Now, what I notice is x minus 5 and x minus 5 divides to 1. 12 divided by 3 divides to 4. Over here, x minus 5 divided by x plus 5, that gives you 24 over here. And here, 12 divided by 4 divides to 3. X plus 5 divided by x plus 5 divides out. So now what I'm left with is 4 times 2, which is 8, over 12 times 2 is 24. And this just becomes plus 3. Well, now can I add 24 and 3? Yeah, sure. Of course you can. That's it. Important things to understand about these problems. And what we basically have for a complex fraction here is we have a fraction in the numerator, fraction in the denominator. All right? And then also we have this larger fraction that's going on. So my idea of this is that's too many fractions, right? Especially if I'm looking on my phone, I can see that there's way too many fractions for one problem. So if you guys remember for rational equations, what we did to eliminate the fraction was multiply by the LCD. And you could put these numbers here over 1, and you can recognize that the LCD is just x minus 2. So my preferred method, same thing as like solving equations, I'm going to multiply everything times x minus 2. Everything. All right? Now, I'm not going to rewrite that because hopefully we can do a little bit of this in our head. If I multiply x minus 2 times 4, I'm just going to be left with 4 times x minus 2. If I multiply x minus 2 times 1 over x minus 2, you guys can see that the x minus 2's will divide to 1. Just leave me with 1. Then, in the denominator, x minus 2 times 3 is just 3 times x minus 2. And x minus 2 times a negative 1 over x minus 2 is just going to be a minus 1. Does everybody see that? By multiplying by the LCD, do you guys see how I just simplified this now just to one fraction? Yeah. Right? That's the power of multiplying by the LCD. Now, I'm just going to apply a little distributive property to get rid of my exponent. So I get 4x minus 8 plus 1, and then all over 3x minus 6 minus 1. And then I can simplify this one more time. 4x minus 7 over 3x minus 7. Can I divide out the negative 7s? Yes. No. Guys, you can only divide out terms when they're separated by multiplication. Order. Okay, these terms are separated by subtraction. Doesn't work. Like for instance, 1 minus 7, 1 plus, or 2 minus 7. Is that just equal to 1/2? No, that's equal to negative 6 over negative 5. Right? That's not equal to 1/2. Correct? Or negative 1, or yeah, positive 1/2. Right? It's not the same. You can't just divide those out. So anyways, that's it. Now, let's go a little bit step further. Because one thing we talked about in the first day of this chapter was identifying the restrictions, the values that x cannot equal. So let's go back to the original problem, because we're going to want to look at the restrictions from the original problem as well as from our simplified problem. So when we look at the original problem, we realize that x cannot be a certain number, right? Because that would not be in the domain, or that would be a restriction. So what value can x not equal in this original problem? 2. And then what about here? What value can x not equal? Well, what happens when we set 3x minus 7 equal to 0? We get 7/3. OK? We have 2 fractions. We have fractions in the numerator and fractions in the denominator. Now, this is, again, another example of a complex fraction. And if you guys remember when we first did complex fractions, if you guys remember in your last focus lesson, not the one today, but in the last 2 class periods ago, what we did to get rid of complex fractions was we multiplied by the LCD. And guess what? You could add these if you like, and then subtract these if you like, and then combine them. But my best thing is whenever I have variables in the denominator, I want to get rid of all my variables. So what I'm going to do is I'm going to determine my LCD, and I'm going to multiply everything by my LCD. So the LCD, or least common multiple of my denominators, which we call least common denominator, is going to include
X plus 5
Does x plus 5 divide into that?
Sure.
Yeah, it goes in there x minus 6 times. Does x minus 6 divide into that? Yeah, it goes in there x plus 5 times. OK? So both of my denominators, or all of my denominators, divide into that expression. Do you want me to re-explain that another way?
Yes.
OK. Basically, guys, again, as I mentioned, x, all I'm saying, if it's a multiple, right? Think about remember when I did 3 and 6? I said 3, 6, 9, right? 6, 12, 18, right? I said the common multiple was 6. Because does 3 go into 6? Yes. Does 6 go into 6? Yes. So you take your common denominator, and you say, hey, does x plus 5 divide into that? Sure it does. X minus 6 times, right? And then you say, does x minus 6 divide into that? Sure it does, right? Because that divides the 1. It goes in there x plus 5 times. So do you now agree with me that all of these divide into that common denominator? That's why just multiplying the denominator is so helpful when you have polynomials, because it's always going to produce you something they divide into. So now I'm going to multiply everything by my LCD. No. Oh, you need me to help you out? Oh, sorry. Trash can's over there. I know it's sometimes hard to get over there. So you have to multiply your numerator and your denominator by your LCD. Remember equivalent? Remember, see how I multiplied the numerator and denominator? I'm going to do the same thing over here, but my goal in this case is not to produce equivalent denominators. My goal this time is to eliminate the denominator. Now, notice how this is an expression. This would be like x plus 4 or something. You have to multiply times both of them, right? You can't see how these are separated? 5 times x plus 4. You have to apply distributive property, right? These fractions are separated by addition and subtraction. You have to apply distributive property. Yes? Right? So in reality, I'm just going to write it over here to make it more sense. So I'm going to say the product of this times that, and this times that. Now, let's have fun using the zero product property. Once you understand, you take for complex fractions, when you have an expression divided by another expression with fractions, multiply everything by the LCD. Let's see what happens. Well, here, x plus 5 divides into it, right? Here, x plus 6 divides into it. Here, x minus 6 divides into it. Here, x plus 5 divides into it. So now I'm left with 4 times x minus 6 plus 9 times x plus 5 all over 5 times x plus 5 minus 8 times x minus 6. Do you see how I have no more fractions anymore? I mean, I just have one general fraction. That's it. And then you guys can just go ahead and simplify your work. Apply distributive property, apply distributive property. Final answer is 13x. Let's see, that's going to be, whoa, cross what up? Over here? We can't cross the x plus 5s out because look at what these terms are separated. They're separated by addition and subtraction. Remember, the division property only works. See how everything is separated by multiplication and division here? That's why I can apply the division property. But once you separate terms and expressions by addition, you can't apply the division property.
13x plus 21.
Plus 21.
Negative 3x.
Okay. And you can't factor anything else out from there, simplified. Okay? That I did last class period. Except now, not only do I have a fraction in the numerator and the denominator, but now I have them separated by addition and subtraction in the numerator and denominator. However, so whenever you guys are adding and subtracting, or especially when you guys have complex fractions, the best thing I want you guys to do is, one, identify the LCM, and let's get rid of this crazy stuff that we have going on in the numerator and denominator. So to get rid of these, all I simply need to do is multiply every single term by my LCM. So let's figure out what the LCM is. Well, here I can factor this. Difference of two squares tells me this is a factored form of x minus 3, x plus 3. So if you guys look at this, the common factor, or the common multiple for all of these has to contain at least an x minus 3 and an x plus 3. Does everybody agree with me? So my common multiple is x minus 3 times x plus 3. Now, all I'm simply going to do is basically you're multiplying your LCM and your numerator and your denominator. But when you do that, since they're separated by addition or subtraction, you have to apply distributive property, correct? So in reality, you guys are going to multiply everything by your LCM. And since you're multiplying, that means everything is separated by multiplication. So since they're separated by multiplication, you can apply the division property. OK? So now we just had the war of division property. Let's clean up and see what we have left over. I have 2 times x plus 3 plus 3x. That's left in the numerator, right? Because I factored those out. Right? That's all I got left. Denominator, I have 3 times x minus 3 minus 4x. So we don't need to be lazy. We can do this. 2x plus 6 plus 3x. 3x minus 9 minus 4x equals 5x plus 6 over negative x minus 9. And there you go. Welcome. All right, so this problem is very similar to the problem I just did, except for now, rather than just having one variable, now we have an expression. We have a binomial. So still, it's the same case. We need to look at this. When we have this 2, it's being divided by x minus 1. So we need to undo dividing by x minus 1. So to do that, we're going to multiply by x minus 1. And since this is a denominator, we're going to multiply it by in our numerator. And whatever we do on our left side, we need to make sure we do on our right side, right? Now, you can put those over 1 if you want to, but we should understand that they're just both going to be in the numerator. All right. So now what's helpful about multiplying by this is we know that now these are going to divide to 1 because they're the exact same binomials, right? X minus 1 divided by x minus 1 is just going to give you 1. So that's going to leave us with 2 equals. Now here, I'm multiplying my variable times a binomial. I need to make sure I apply my distributive property. So that leaves me with a 4x minus 4. Now, I'll add a 4. So I get 6 equals 4x, divide by 4, divide by 4, and x equals a 3/2. So there you go, ladies and gentlemen. That is how you solve your rational equation. Thanks. The way to determine the LCD, ladies and gentlemen, is just simply multiply your denominators. All right? That's not always going to provide you with the LCD. You want to make sure that if you can factor them first, maybe they see if they have any common terms. But a lot of the, more likely, here, the LCD, guys, is just their product. So we'd write LCD equals x plus 3 times 2x minus 1. Now we know what the LCD is. I'm now going to multiply both of my expressions by that LCD. Does everybody see what I did? Yes? OK. Now, what we notice is what's important about this is, again, the whole purpose of solving rational expressions is to solve them without the rational, without the fraction. So x plus 3 divides into our LCD 2x minus 4 times. And then this divides into x plus 3 times. So now I have this equation. Do you guys see that? Yes. I eliminated my fractions by multiplying by the LCD. That's what you guys need to write down and make sure you remember to do. Find your LCD and multiply it by every term. That eliminates your fractions. We're trying to eliminate the fraction here. Where over here, we're not trying to eliminate them. We're trying to combine them. So that's why I multiplied the LCD on the top and the bottom, so we had the LCD for both expressions. Well, now I apply distributive property. 8x minus 4 equals 10x plus 30. Then I always like to get the x's on the same side first. So what I'll do is I'll subtract an 8x, because I always like to make my x's positive. It's OK. You did the same thing. You did it correctly. Or maybe not. Then I'll subtract 30. And I have a negative 34 equals 2x.
Oh, so either way, it's going to be.
Yep.
Oh, it's going to be second. Jay, you're supposed to think about it.
So in this example, you guys can see we have x plus 2 divided by x minus 4 divided by.
Mr. McLogan,
Yes.
could you please send Jake Swisher to the front office to check out, please?
OK. Just make sure you write down your homework, OK? And I'll put this online as well. So, ladies and gentlemen, when you're looking at a problem like this, do you guys remember the problems that we wrote down last class period, where I saw it was basic fractions, but we had like a variable in the denominator, right? You guys remember that? OK. So the main important thing, whenever you're solving, the main thing we got to do is get these variables off the denominator. So to do that, what we're going to want to do is multiply every single term by the LCD. So we have to figure out what the LCD is. Now, in our focus lessons, we practiced. Remember when we were adding and subtracting, right? With unlike denominators, we had to find the LCD. Or when we were doing complex fractions, basically what we did was multiply everything by the LCD, which is the same thing. So the first thing we want to do is factor anything that we can. Always factor. That's going to be simplifying this. So now you guys see x squared minus 1, I factored using difference of two squares as x minus 1, x plus 1. OK? So now I need to find the polynomial that both x minus 1 and x plus 1 and x all divide into. Agreed? OK. So my LCD is going to be x times x minus 1 times x plus 1. Do you guys agree with me that every single one of my denominators divides into that LCD? Yes? OK. So now, how do we use that LCD to help us solve? Well, if we multiply every single one of our terms by our LCD, we can use the division property to simplify. So what I simply do is just write it multiplication times every single term. All right, see ya. So let's see what happens using the division property. X divided by x, that divides out. Whoa, 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 whoa. Oh, I'm an idiot. I wrote the wrong problem down. I'm sorry. Sorry about this. Hold on. Sorry. This problem was x squared minus x. Sorry. So therefore, this gets factored into x times x minus 1. Sorry. I don't want to like over make this problem. I just realized I'm like, this is going to be an issue. We're going to have a cubic. And not like you couldn't do it, but that's just going to make this problem much more difficult. So anyways, this gets factored down to x times x minus 1. Therefore, my LCD is x and x minus 1. Does that make sense? OK. So if I multiply everything times x times x minus 1, my x's divide out. Here, my x minus 1's divide out. And here, my x's and the x minus 1's divide out to 1. So therefore, now I'm left with an x minus 1 times x plus 2 minus 4 times x equals negative 2. Does everybody follow me? Anybody have any questions? Are we OK? I'm just waiting for questions. We're good. Kind of. Now, apply FOIL here. You get x squared plus x minus 2 minus 4x equals negative 2. I realize this is a quadratic, so I'm going to get all my terms onto the same side, right? So I'll add a 2, add a 2, and I get x squared, let's see, minus 3x equals 0. Now, yes?
When you have the 4 up there, it has to be 4 with the x.
Well, the x minus 1 is divided out, so that's x. Now remember, what am I doing with this LCD? I'm multiplying the LCDs, right? So that's really 4 times x. Okay. Has everybody followed me so far? Anybody have any other questions? Now, yes?
What is this called? Like, what is this?
We're just multiplying by the LCD. We're solving rational equations. It's the same topic that I started with last class period, so that's why I didn't write it up there. Now, in this case, we don't really actually have to factor using a trinomial or quadratic formula. This one's actually not that bad. I can just factor out the x. When factor out an x, I'm left with x minus 3 equals 0. So I can say x minus 3 equals 0 and x equals 0. So my solutions in this case is 3, 0. However, when you're going back up to your problem, you got to make sure you plug your answers back in. Because remember when we were graphing rational expressions, the first thing we did when graphing a rational expression is to do what? It's the first thing we do. Find the what? Vertical asymptotes, right? The points where the values are not a part of your domain. If you guys take your solutions and you plug them in and they make your denominator equal to 0, they're not a part of your domain. So you guys can see 0, when I plug 0 in, that makes that denominator and that denominator 0, right? So 0 is not actually a solution. And the mathematical word we call that is extraneous. Nope, so that would not be a solution. Because when you plug 0 back into your equation, it makes the denominator 0. You can't ever have your denominator equal to 0. So you always want to make sure you guys go back and check your answers. Welcome. So what I want to do is talk to you a little bit about why we have restrictions on our domain when we're solving rational equations, as well as what are extraneous solutions and how do we get them where they come at. Now, I don't know if you've taken, depends if you've taken the graphing course yet or if you're about to take it, but one thing I want you to understand, when we're dealing with rational equations or the reciprocal, we're going to have these things called asymptotes or holes. And I'm not going to get very detailed into them, but because that's more for the course on graphing. But one thing I want you to understand is when we're looking at something like that, and let's actually say here's a hole. Okay. So when we're looking at kind of like identifying the domain of a graph of a rational equation, or a rational function. What I want you to understand is these dotted lines are what we call asymptotes. And that means our graph is not going to be a value at those lines. So here you can say that x cannot equal 2 at this value is an asymptote. And this is where the graph is going to approach. And I have other videos on what exactly asymptotes are. And then you could also see that x cannot equal 3 because that's a hole. And there's a difference between holes and asymptotes. But their similarities are that both of them, your values are not solutions of your equation. So let's go and look at, well, how do these even come about as an equation? Because I can kind of see, all right, in a graph, wherever there's that dotted line or there's an open circle, that's a hole. They're not a part of the solution. OK, I kind of get it. But how do we identify that in an equation, and how do we find them? So we spend a lot of time when graphing is finding the holes and finding the asymptotes. But you have to have a general understanding when we're solving rational equations, because sometimes, even though we find a solution, our solution could be what the asymptote is or the hole. So we got to make sure we know how to identify them. And the best way to know how to identify them is with the basic understanding that, a divided by 0 is undefined. Right? Anything divided by 0 is going to be undefined. You can't divide 0 into any number, no matter what the number is. So if we have this basic understanding, when we're looking at a rational equation, what we want to do when we're looking at a rational equation, even a crazy one like this, I just made it up. But if we're looking at this, what we need to understand is, all right, well, what I'm going to do is I'm going to put restrictions on my domain, restrictions on my solution, saying this, I don't know what the answers are, but I know when I get the answers cannot be these values. And the values that I'm going to choose are x cannot equal 1, x cannot equal 3, or negative 3. And x cannot equal negative 5. Now, why am I choosing these values? Well, if I take 1 and I plug it in for x, you can see that 1 minus 1 is going to be 0. Therefore, that is going to produce an undefined value, which we call an extraneous solution. If I plug negative 3 in for x, you can see here it's going to create 0. And if I plug negative 5 in for x, over here it creates 0. So anytime we have a value that can create 0 in our solution, it is either going to create an asymptote or a hole, and the solution is going to be extraneous. Now, the difference I'll go through real quick as far as a hole and an asymptote. Hole and asymptotes are very similar, but the difference between a hole and asymptote is we can actually factor out, for instance, like if I had something like this with my equation, we can factor out the x plus 3, correct? Therefore, even though that's still a restriction, my value x can still not equal negative 3. However, it's going to produce a hole, not actually an asymptote. But why is this all important? Well, this is, again, important because when we go ahead and find our solutions, right, we're going to apply the operations to solve this rational equation. And once I get my values, I'm going to get some certain answers. What I want to do is go back to my original constraints and say, all right, are any of my solutions these values? And if they are, our values are extraneous and they're not actually going to be a part of them. So it's very important to check your answers. Go back to your original constraints and see if it was there. And there we go, ladies and gentlemen. That is why we put restrictions on. And that is just a little bit of a definition of extraneous roots as well as introduction to asymptotes and holes. Thanks. All right, so in this example, you guys can see we have variables in the denominator, right? And we're solving, right? So therefore, the same just thinking I did on those two problems. I know this says polynomials and so forth. But all we're going to do is multiply by the LCD. But before we do that, we always want to simplify. So you guys can see I can factor this, right? What two numbers multiply to give you 3, add to give you negative 4? Oh, this is actually the same factors. But just factor that out, because what that does is that helps us out. Because if you guys remember in the last one, remember that one where all we did was to find the LCM, we just multiplied every single denominator, right? Well, you would not want to say your LCM is going to be x minus 1 times x minus 3, and then multiply x squared minus 4x plus 3. Can you guys see what problem that would be? Right? So factor this. So therefore, you can see, hey, guess what? These are redundant. right? They already show up. So of course they're already in the LCM. So my LCM is just going to be x minus 1, or LCD, x minus 1 and x minus 3. Because I factor this down, and those two are there, right? So that's helpful. That's good. So always factor before you determine your LCD. Then, just like I told you before, let's multiply everything by our LCD. No. No. OK, so what's nice about doing that is just like I told you guys when we were simplifying. Remember when we were adding and subtracting, simplifying, and all that stuff we did in this class period? We can now apply the division property. Whenever you have a term or an expression or a variable divided by itself, it goes to 1. X minus 1 divided by x minus 1 is just 1. But again, what I just said only applies when they're separated by multiplication, right? Do you guys see how those are all separated by multiplication? Yes? OK. Here, the x minus 3's divide out. So anyways, I'm left with a 2x times x minus 3. Here, I'm left with a positive x minus 1. And here, the x minus 1's divide out, and x minus 3's divide out. So I'm left with a 2. That's it. Huh? Cross multiply what? To do that, if you were going to apply cross multiplication, you would have to combine these. Did I show you how to add two rational expressions? Yes, but since they don't have two denominators, you would have to get common denominators, combine them, and then apply cross multiplication. But in my same fact, I still would not want to do cross multiplication. That's just as much work as doing this. My main mode of thinking, whenever you guys have a rational expression, find the LCD and multiply every single term to get rid of it. Now we have an equation. Can we solve this? It might be difficult, but we can solve it, right? First, we apply distributive property. 2x squared minus 3x plus x minus 1 equals 0. I notice that this is a quadratic, right? So for us to get a quadratic, I got to get everything to, no, wait, it's equal to 2, right? I have to have everything equal. I have to get everything to the same side. So I'm going to subtract the 2 on both sides. And then I'm going to combine my like terms, which I get 2x squared minus 2x minus 3 equals 0. Yes, good job. Negative 6x, so then that would be a negative 5x, right? Yes? OK. So, ladies and gentlemen, there's a couple ways that we've discussed in this class, right? You could try to factor this. You could use the quadratic formula, right? There's a lot of different ways in your phone, though. Doesn't really do as much, or at least won't allow to be used in your phone. But on your homework, you could definitely. That was the hint. But you could use quadratic formula. You could graph it, find the intercepts, and so forth. But this one looks like it should be hopefully quickly, easily be factorable, because there's only two terms that can give us 2x squared. And that's going to be 2x and x. So now all I simply want to do is go ahead and determine what two numbers multiply to give me negative 3. That's also going to give me a negative 5x. So it's either 3 and 1 or 1 and 3. We know that one of them has to be positive, one of them has to be negative, though, right? Because they're multiplying to give you a negative 3. So the 3's there or a 1's there, or it's a 1 and a 3. And when I calculate the inner and the outer, what I notice is if I did 2x times negative 3, that would give me a negative 6x. And then if I added that to 1 times x, which is 1x, that would give me 5x. So I factored it down to 2x plus 1 times x minus 3 equals 0. And then I apply the zero product property to x minus 3 equals 0. And then x equals negative 1/2, and x equals 3. However, I'm still not done. Because as you guys remember when we were talking about these graphs, when we were like graphing them, what's the first thing we found out with the graphs? What's the first thing we found out about the graphs? Step number 1. What's the first thing we find? Anybody? Vertical asymptotes. What is the vertical asymptote? The vertical asymptote, what makes the denominator equal to 0, right? The vertical asymptote is not a part of the domain. It's that vertical line. You cannot graph it. So whenever you find your solutions, you have to make sure you go back and take your answers and make sure that they do not make your denominator equal to 0. And guess what? When I take my solution 3 and I plug it back into my equation, I'm sorry, when I take my solution 3 and I plug it back into my equation, I'm sorry, one more time. When I take my solution 3 and I plug it back into my equation, you can see that I get the denominator 0, right? So therefore, this solution is what we call extraneous. It's not actually a part of the domain. Even though it's a solution, it's not a part of the domain, right? It would actually be like it's not there. It's not actually a point on the graph. So it would just have -1/2, which does not make any of the denominators 0. OK? Again, ladies and gentlemen, when we see a rational expression, we automatically know, OK, I don't want to deal with fractions, right? You offered a thing of subtracting fractions. Hey, if you remember how to do it and you can do it and you're comfortable with it, that's awesome. That's the way you should be. But for the majority of you, you guys just don't even want fractions. You don't even want to talk to fractions. You don't even want to deal with them. You don't want to see them. You want to get rid of them, right? Out of your life. So what we simply need to do is when creating our fractions, let's just get rid of them. So the best way to get rid of our fractions is to multiply by the LCM. So we look at this and we say, what's our LCM? Now, some of you might look at this and say, all right, well, what we've done before is we just taken the denominator for each one of these 3 and said that was the LCM, right? So you guys might say, well, logic might tell you, OK, the LCM equals x plus 5, x plus 3, and x squared plus 8x plus 15. Now, that's a pretty big LCM. And that's going to be a lot to multiply everything by there. But what we want to do is, can we simplify? Always look, ladies and gentlemen, especially when you have a trinomial, can we factor that a little bit further? And of course, what we notice is this can be factored down to x plus 3 times x plus 5. So therefore, we notice that this is redundant, right? LCM says least common multiple. So we don't need to multiply this again. So our LCM then is just going to contain x plus 5 and x plus 3. So now what I'm going to do, yes?
So when x plus 5 and x plus 3 just cancel out x squared plus 8x plus 15?
Yeah, it's because they're the exact same, right? So they're just going to divide to 1. So we'll get that in a second. So now I need to multiply every single term by my LCM. I guess I already had this one conversation before, but I guess some students maybe didn't understand the directions. OK, so now what we look at this is we notice, all right, so if I was going to multiply this times that, I notice that my denominators divide to 1. So I'm just going to be left with 2x times x plus 3. We already talked about how this factored down is this. So we know they're exactly the same. So if I divide the same expression over the exact same expression, that divides to 1. So therefore, I'm just left with x squared minus x plus 10. Notice my inclusion of the parentheses. OK? You're subtracting this whole term. So you're subtracting x squared minus x plus 10. So I want to put parentheses in there so I remember that. Then when I go over here, I notice x plus 3 divided by x plus 3. That divides the 1. So that's going to equal 3 times x plus 5. OK? Now, ladies and gentlemen, we can apply distributive property. So therefore, I have 2x squared plus 6x minus x squared plus x minus 10 equals 3x plus 15. Whew. It's a big multi-step equation, right? Taking you back to Algebra 1, flashbacks. Wow. OK. So now, before we can combine like before we get our variable to the same side, let's combine like terms. So I know my x squareds I can combine, my x's I can combine. So therefore, I just left with x squared plus 7x minus 10 equals 3x plus 15. And automatically, ladies and gentlemen, I noticed that this is going to be a quadratic, right? Because I still have an x squared. So rather than just saying, oh, I'm going to get my x by itself like we did with the linear equation, now I need to set this up as a quadratic. I need to set this equal to 0. OK, so now I will get everything over to the same side so it's equal to 0. So I subtract 3x. and let's subtract 15. So make sure you guys do that on the same side. And therefore, I'm left with x squared plus 4x minus 25 equals 0. And I don't remember having that as my answer. OK, where did I go wrong? It's plus 15. Well, I have a positive 10. Oh, this should have been, oh, I wrote the problem wrong. My bad.
Mr. McLogan. You are something.
There you go. Sorry about that. I knew I was looking at it. I'm like, where did my problem go wrong? So now, there you go. No. I'm sorry. X plus 5, x minus 1. So therefore, now I can apply the zero product property and say x equals negative 5 and x equals positive 1. OK? Cool? Amazing? Good. So on this next one, this one gets a lot of students because what they automatically want to do is, again, multiply your two numbers. And again, as I talked about, when I say, what is the LCD of 2 and 9? That's 18. And then I say, what's the LCD of 3 and 9? And they say, oh, 27. No, the LCD of 3 and 9 is actually 9. In here, guys, we can factor 2x plus 8. If I factor 2x plus 8, I can get that as 2 times x plus 4. Therefore, the LCD in this case, the LCD of this problem is 2 times x plus 4. So all I need to do, when I multiply that times every single term, 2 times x plus 4. I multiply this, 2 times x plus 4. And then this one, 2 times x plus 4. What happens is my x plus 4s divide out. So I'm left with 4 times x plus 7 minus 4 times x plus 4 equals the 2's divide out, the x plus 4's divide out. So I'm just left with 2x plus 20. Again, apply distributive property. So therefore, I get 4x plus 28 minus 4x minus 16 equals 2x plus 20.
Today at 6:30, senior men will play the faculty in a basketball game. Bring your whole family. Proceeds are going to the Wolfson Hospital Teen Division, and tickets are $3. This Friday will be our talent show at 6:30 in the auditorium. Tickets are $5. You can get them from Mr. Crawford now, as well as at the door.